Welcome everyone, welcome to our Leonhard Obermeyer Center Day 2021. In the next 30 minutes, I will give you a brief overview of our activities over the last year. First of all, I'm very happy to announce that we have a new premium member, which is Innovationsmanagement Bau GmbH, a company that is actually comprised by 8 companies, construction companies, that are interested in doing research and innovative developments in the field of construction. And this is exactly what we do, so we are very happy that we have them as new member in the LOC. So this brings us to this general overview of the LOC. The Leonhard Obermeyer Center is the TUM Center of Digital Methods for the Built Environment, consisting of 5 groups at the TUM, or 5 chairs, namely Architecture Informatics, headed by Professor Petzold, my chair, Computation Modeling and Simulation, the chair of Construction Process Management, headed by Professor Nübel, the chair for Geoinformatics by Professor Kolbe, and Photogrammetry and Remote Sensing by Professor Stiller. Together we are more than 70 researchers in this field, which makes us one of the biggest centers in this regard in Europe. We work very intensively together within the center, but also with external partners. So we have an intense collaboration with the construction industry, with the software industry, but also with non-profit and governmental organizations. So let's have a look on the right-hand side here. In the upper part, you see our premium members, namely Nemetschek Group, Obermeyer, Allplan, and the CADFilm Group, and our new premium member, Innovationsmanagement Bau GmbH. Then we have the associate members in the middle, Autodesk, Bauindustrie Bayern, Dassault Systèmes, Dresden Sommer, SSF Ingenieur, and Sophistic. And in the lower part, you find our non-profit and governmental organizations that we are collaborating with our partners. So let's now come to the highlights over the last year. One of the most important highlight is that the LOC has a new sister institute, which is the TUM Georg Nemetschek Institute. It was launched in December 2020 thanks to a very generous donation by Georg Nemetschek, and that's really, really impressive. The topic of the Georg Nemetschek Institute is artificial intelligence for the built world. So it's kind of related to what we do at the LOC, but with a very strong focus also on artificial intelligence. Luckily, we have a strong involvement of key persons in the 2 institutes. So many professors of the LOC are also involved in the Georg Nemetschek Institute, especially in the Scientific Advisory Board. So we actually are working already on a very strong collaboration between these 2 sister institutes. We had a very nice inauguration symposium in April this year, where we invited 20 of the best researchers from the entire world in this field, AI for the built environment. They gave very interesting, insightful presentations about their current research activities with respect to AI for the built environment. We had very intense discussions, exchange, although it was an online event, but nevertheless, we really enjoyed this event. So this was the Georg Nemetschek Institute, but let's now come back to the LOC, and I would like to highlight the PhD projects that have been finished within the LOC. So first of all, I would like to mention Marco Häusler, who has successfully defended his PhD in September. His work was sponsored by Obermeyer. He's actually a member of the Obermeyer group. And his topic was model-based quality assurance in railway infrastructure design. So we all know that in railway design, we have to follow a large number of guidelines and rules. And he developed a method to encode these rules in this visual language that we see below, and make it possible that models that have been created can be automatically checked against these rules and regulations, which of course improves the quality of the models created in the design process. A second completed PhD project was by Kanishk Chaturvedi. His PhD topic was on integration and management of time-dependent properties with semantic 3D city models. On the right-hand side here, you see in the upper part the typical 3D city models, buildings, transportation objects, and so on and so forth. Normally, they have static properties, static attributes, but we would like to integrate dynamic data coming from this lower part here, coming from sensors, databases, and sometimes even from external files. Kanishka has worked on creating a methodology to integrate this with the city models using the concept of so-called dynamizers. And then the third PhD project, again with another topic, reflecting quite well the range of the different topics that we cover in the LOC. This is a PhD project by Rong Huang. Her topic was change detection of construction sites based on 3D point clouds. So she took point clouds from different snapshots over the construction process, compared these point clouds, and could find out where are the changes, and then also had a semantic interpretation of these changes, so including the detection of arbitrary objects on the construction site. Okay, so this was the PhD defenses, the finalized PhD projects, which of course is one of the most important aspects of our work in the LOC. But we have many, many other research projects, and I will now come to them. One project that was recently finished is a project that we have done together with RPlan, and it's about deep linkage of drawings and BIM models. So what is the background? Well, in the construction industry, we are still heavily relying on 2D technical drawings. We see them everywhere, essentially. At the same time, BIM is more and more adopted. So what we typically have now is hybrid projects, where both models and drawings are delivered by the architects and the engineers. So now it's important to check the consistency between the 2D drawings and the BIM models, because we will have to find out whether they really fit with each other. To do this, we developed a methodology where we first of all use shape descriptors to find the location and the orientation of the floor plan within the 3D model. So this is the first step. And the second step is then that we use AI methods to detect elements in the 2D drawings, like for example the doors, the windows, and so on, and match the same objects in the 3D model. And by doing so, we can really bring them together, link them, and deliver a smart container where we have these links available for any kind of analysis. Another project that I would like to highlight is a new project. So we are kind of at the other end of the life cycle of these research projects. This project is about big data in construction execution. It's funded by our new member, Innovationsmanagement Bau GmbH. And here we are investigating on-site activities with respect to productivity, but also with respect to safety, using big data approaches. We use a multi-sensor approach, so we take photos, we use photogrammetry, we do laser scans, and we also have thermal cameras on the site. We take these data, the information generated by these different sources, fuse them, and then apply big data approaches to find patterns in the data. Luckily, we have direct access to a demo site in Regensburg. This is the so-called building lab, which is currently being constructed by the Bavarian Construction Industry Association for the University of Regensburg, the University of Applied Science, Regensburg. Very interesting new project. Related to this, topic-wise at least, is another project which is supported by Field Data.io, a very interesting startup here in Munich. This project has the title Construction Site Monitoring using AI-supported process data acquisition. It's about improving the monitoring of the construction sites. Here we use AI-supported process data acquisition and then apply neural network pattern recognition for identifying individual steps in the construction process. As I said, the resulting system is implemented in cooperation with Field Data IO. Then I come to another project, very interesting project, again a project that just starts right now. This one is funded by this new Geoinformatics Institute that I already mentioned. The project is called AI for Twinning, and it is about the automated creation of so-called multi-scale digital twins. We have a number of principal investigators that are professors also in the LOC, namely Professor Petzold, Stiller, Kolb, and me. And we have two other professors of TUM, Professor Kremers from computer science and Professor Schuh from aerospace engineering. Together we use, again, multi-sensor, multi-resolution data, including images taken from airplanes, including also radar data, including laser scannings, images, thermal images, and so on. We bring them together, combine this with domain knowledge about the structure of buildings, and then come up with a system of interconnected digital twins across the different scales. So this is really the vision here, to have different resolution levels and have a consistent way of representing these different digital twins on the individual levels. Another project also related to artificial intelligence that just started right now is on code compliance checking. This project is funded by the International Graduate School of Science and Engineering, the ETHZ. It's an international ETHZ project between TUM and Technion in Israel. So we work together with Professor Raphael Sachs, who is really an expert in BIM and also in AI. The idea is to check buildings for compliance with certain regulations, like, for example, fire safety, accessibility, and so on. But what is really new in this project is that we are also working on model healing. This refers to the fact that quite often the building model does not comply to the regulations, and then we propose to do changes, systematic changes in the building model to find valid solutions that are close to the original model in case of any violations, but then fulfill all the regulations and all the codes that have to be applied. Another very, very large project where we are right in the middle of doing this project is on additive manufacturing in construction. So this is the so-called DFG Transregio 277, a very, as I said, very large project with more than 40 researchers being involved. It's a joint project by TUM and TU Braunschweig with very strong participation also of the LOC. So the principal investigators here are Professor Petzold, me, Professor Rank, and also Dr. Kollmannsberger. We work on different topics, but in general, we are focusing on integrating the design process with the manufacturing process, doing diverse kinds of simulations to support this, and also implementing the concept of digital twinning, meaning that we capture the resulting geometry of the printed object and then feed it back also in the digital model. This is only a rough insight. We will later see in a presentation exactly about this Transregio where we go more into detail. Another project that runs already for quite some time is change detection based on image sequence and BIM compliant indoor models, a project in cooperation with the University of Applied Science in Würzburg and the Bavarian Academic Forum. Here we are researching model-based 3D reconstruction using photogrammetry with a very high level of geometric quality that meets the typical metric tolerances in construction. So this is really an increase in quality. Another project is our BIM for factory. Here we extend the concept of BIM now for factory plans. So we integrate extensive information about the production systems, the assembly lines, and all the equipment in the factories. We also use augmented reality to do an early validation of the different design alternatives that we have. So we can go on site into the factory and check the different design alternatives in an interactive manner. This project is done in cooperation with Fraunhofer, and it has started in December 2020, so it's right in the middle, and we will see more results in this project very soon. Another project is on the standardized approach for real estate development decisions. So this is something very early in the chain of doing a construction project. Here the investor needs to take a decision whether he wants to realize the project or not in exactly a very early project phase. And the approach here is to standardize real estate properties according to their later utilization using a big database. On the basis of this standardization, then key parameters of production and operation are extracted, like construction costs, construction time, and operating costs, which is the most important basis for any decision. And based on that, then the investor can take his or her decision now really based on evidence and not so much on gut feeling. Okay, this brings us to standardization. When we speak about standardization in LOC, it's often about data model standardization for data exchange, and we are collaborating with two major standardization bodies on the international level. On the one hand side, Building Smart International. On the other hand side, the Open Geospatial Consortium. With respect to Building Smart, we are heavily involved in extending the standard industry foundation classes for infrastructure. And we are really happy that after many years of work, we are really close now to the official release of IFC 4.3 candidate standard. This standard will comprise all the extensions that we have worked on, including bridges, roads, railways, ports, and waterways. In all these different projects, the LOC was involved with their members. Another project that is related to that but not yet finished is the IFC Tunnel project. It's currently running. I'm acting as the technical lead in this project. Here again, we would like to extend the IFC data model with respect to specific kinds of geometry, for example, sweeping. Very important also, of course, in tunneling is geology and geotechnics. We are also working on creating new elements for excavation and excavation support, and also for the very specific equipment that we have in tunnels. Here, phase 2 has started early this year. After we have defined the requirements in phase 1, we will deliver a draft standard by the end of 21, and hopefully end of 22, we will then provide the candidate standard. In all these developments in Building Smart, of course, it's very important to have also the vendors, the software vendors on board. And in this respect, we are very happy about an ongoing collaboration with Autodesk. So we are helping them to shape the standard on the one hand side, and on the other hand side also to implement the standard. And well, Sebastian Esser was funded by Autodesk for a number of years, supported by Autodesk. And in this frame, he has developed the IFC Infra Toolkit, which now facilitates Autodesk to integrate these new standards into their product. Okay, I talked about Building Smart and OGC, so the other part is the Open Geospatial Consortium, and here I'm very happy to announce that now the CityGML version 3 conceptual model was officially adopted and issued by the Open Geospatial Consortium, so it's now a public standard, an official standard, after, again, many years of work on this standard. For those that do not know CityGML, it's an international standard for semantic 3D city and landscape models, and also for urban digital twins. So congratulations for that. Thomas Korber was involved there quite intensively. Okay, this brings us to the awards. Luckily, we receive from time to time awards for the work that we do, both in science but also in standardization. And I'm very happy that, again, we received a number of awards. So, for example, at the University Awards by the Bavarian Construction Industry Association, we were quite successful. LOC members won all 3 prizes. The first prize went to Cornelius Breidel, a former PhD student by me, funded during his PhD by Alplan. He received the first prize here for his PhD. The second and third prize went to master students in LOC, Laura Wilhelm and Yarjun Bolik. Then we have an outstanding paper award, which went to Son Nguyen for a paper presented at the 3D GeoInfo conference. We have a runner-up best paper award that we received at the ETHZ conference for Fiona Collins, who is the Geoinformatics Scholarship holder in the moment. We have received the Thorpe medal, also by ETHZ, Alex Braun and me, for a paper that we recently published. And we have received the Building Smart Award for exactly the IFC Infra Toolkit that Sebastian Esser has developed and that I recently mentioned. We were also quite successful in the competition, the national competition of IT Gebaut, which is organized by the Ministry of Economic Affairs in Germany. And you see we have in total 5 awardees also in this competition, which is also very nice. And then I'm very happy also to announce that we were successful in a challenge, an international challenge on computer vision in the built environment, which was organized in the frame of the IEEE conference on computer vision and pattern recognition, a really important and well-known conference. And the challenge was that our members in the LOC, they have received point clouds of certain buildings, and they were supposed to process these point clouds and come up with 2D drawings and 3D models, in the end, BIM models, as a result. And these were then compared against their metrics, and I'm very happy to announce that we received the second prize in this competition. Congratulations to all these prize winners. Okay, this brings us to education, because you have also seen that many of the awardees were students. So education is definitely very important. And in this context, I'm very, very happy to announce that the LOC Master of Science in Information Technologies for the built environment that we have designed and developed over the last 2 years has now been officially adopted by the TUM Senate, so it will become reality, which was quite some work to get there. The background is, well, as we all know, the AEC industry is short of staff with advanced skills in digital methods, so this master program is supposed to fill this gap and educate students across the traditional disciplines like architecture, civil engineering, and also geodesy, and well, provide them these advanced skills. We have elaborated a study plan. You can find them here on the right-hand side, and we will start in exactly 1 year. So we now start advertising this master program, and the first students will then start next year. And we are really excited and happy about this new master program. Now to education on another level, the level of continuous education for professionals. Also there we are very active in the LOC. And now in the frame of the TUM Institute for Lifelong Learning, a new institute at UM. We have an older program that runs now for 5 to 6 years already, BIM Professional, where we now have the 10th run in this program. So we educated a lot of professionals already with respect to building information modeling. Very successful program. We normally have more people interested in the program than we can really have as participants. So this is the, let's say, old program, but we have also a new program called Digital Twins for Cities, which started this year, also quite successful. We had a lot of attendees, and we will continue with this program. The next round, the first round was in German, the next round will be in English, so we can also attract an international audience for this program. Okay, this brings us to outreach. I'm very happy to announce that one of our LOC professors, Professor Nübel, was nominated as a task force member of the Think 20 group of G20. So I guess everyone knows G20 is kind of the bigger version of G7, or sometimes was called G8. G8, so the leading countries in the world in terms of economy. The task force has the name Infrastructure Investment and Financing, and one of the first things they contributed was a policy brief, white paper, so to say, with the title A New Vision for Infotech Governance and Value Network Integration through Federated Data Spaces and Advanced Infrastructure Services for a Resilient and Sustainable Future. And this white paper now has the role of informing and briefing the G20 to take this into account for their policies. So now on a more local level, but still the national level, we were quite active in helping the Ministry of Transport in Germany to define their master plan BIM for federal roads and highways. Here we defined together with them 3 phases for adoption of BIM in Germany, but we also defined what we called a future picture of digital twins in the area of roads and highways, where we now have a clear vision how to integrate sensors, how to integrate artificial intelligence to come up with the next generation of digital twins and provide them for practical use cases in terms of road management. Even more local, we have also provided a contribution to a study for the so-called Future Council of the Bavarian Economy Association. The study had the title Constructing Our Future, Planning, Building, Living and Working. And well, we contributed, of course, our view on digital methods for constructing our future to have better buildings, higher quality in buildings, but also higher quality in living and working. More local, so we zoom in. We also work with the city of Munich quite intensively. So we provide scientific support for the city of Munich, especially in terms of their urban digital twin projects. They have currently 2 projects. One is the Digital Twin Munich, which is funded by the Federal Ministry of Transport and Digital Infrastructure. Here the goal is to use these digital twins for the very important application scenarios of traffic management on the one hand side, and the other hand side, air pollution control. This is done together by the chairs of Geoinformatics and Traffic Engineering, and they work on a concept for integrating microscopic traffic simulations and highly detailed street space models. So that's the approach there. The other project, also by the city of Munich, is on connected urban twins. This is now funded by the Ministry of Interior, so another federal ministry. Here the goal is to create use cases for urban development and especially for new forms of public participation in terms of urban development using these urban digital twins. Our colleagues here work on standardization, sensor technology, and augmented reality and virtual reality. Then I'm happy to announce that we are also creating a new big publication. Our BIM textbook will be published very soon in the 2nd edition. The 1st edition was published back in 2016. Now a lot has happened since then, so we are now publishing the 2nd edition, also because the 1st edition was really successful. It was sold multiple thousand times. So it's a really good opportunity to now come up with a new and updated version of this book. Another publication is Guidelines, Geodesy and BIM, version 3.0. This is a publication that you can download for free from the internet. This was created in a cooperation between Wundertisch GIS, DVW, and many LOC members have also contributed to this guidelines. Last but not least, I would like to highlight also the new TUM Venture Lab built environment, where LOC is also quite strongly involved. this is a platform for helping and supporting innovative startups in the field of the built environment. And this is also, of course, the mission of the LOC, to not only do research, but also bring the research into practice, into products, for example, by means of startups. And well, as I said, LOC is involved quite strongly. The academic director is Konrad Nübel. The entrepreneurship ambassador is Frank Petzold. And our good old partner, Nemetschek, is also providing sponsoring for this new TUM Venture Lab, which is, again, quite helpful and quite impressive as well. Okay, this was the short introduction and an overview of all our activities. We will now dive more into detail in some of the projects. Let's have a look on the program. We will now directly go to the keynote of Dr. Rohit DUBEY, who is our LOC postdoc, sponsored by the LOC. Then we have a lunch break at 12:30. We come back at 1:30 for the first round of presentations of individual projects. We will have a coffee break at 2:30, then come back for the second round of presentations at 3. Professor Kolbe will then give the final presentation, an outlook and a summary of the day at 4:20, and at 4:40 you are very much invited to join us for the get-together, where we will have some drinks and also some food will be available. So thank you for being here. I hope you enjoy the day, and I wish you a nice day. Thank you.
Okay, thank you everyone. Last year around the same time, I was in Singapore, and I was packing my bag, and I was looking forward to join the community, the LOC community. And it's been 1 year. It's been 1 year here, and I'm very happy that my stay in Munich and the research with the LOC community has been productive. And I'm very happy to present my research with you, everyone here. Okay. So a brief introduction about me. So I'm Rohit Kumar DUBEY, and I did my PhD from ETHZ Zurich, and under the supervision of some great names mentioned here. Immediately after that, I joined the LOC Postdoctoral Scholarship with the chair of computational modeling and simulation. So my research focus lies at the intersection of human wayfinding modeling, architectural design, and artificial intelligence. And the whole goal is, how can we make it towards developing solution for human-aware building design? So let's discuss each one of them individually. So for human wayfinding modeling, my focus is to understand how does different factors in the environment impact our wayfinding skills. How do we navigate from one point to another? And then develop a computational model for that. Then what we do is that we take that computational model and how can we use that computational model in an architectural design tool. And the goal is to facilitate the designers and the architects to solve multiple challenges, which we will be seeing in a couple of slides. And then finally, how can we use artificial intelligence, especially the reinforcement learning mechanism, to come up with new mechanism to develop the decision-making framework of human behavior. One of the major challenges which architects face these days is how can we model the relationship between a building and its inhabitants. And the reason is that there are multiple influencing factors which a human being or an occupant interacts with the building, such as some of them are waiting for the bus, some of them are socializing, so there are multiple numbers of influencing factors. And it can also happen because of the dynamic nature of human behavior. I mean we are unpredictable, so we tend to do certain things which no one can estimate. Although there are multiple existing simulation methods which exist, but they model only the static aspect of human behavior. And while there are many existing simulations that model the aspects of building design, such as energy, its structure, the daylighting, and the wind simulation, but I would like to argue that only Few or almost none models the dynamic nature of the occupants which inhabits that building. So my whole purpose of this talk is how can we involve human being and its interaction with the building, and that will be in terms of wayfinding. So let's come to the concept of wayfinding. So wayfinding is a very common activity. Every human beings navigate from almost on a daily basis. For example, if everyone decided to come here, they had some kind of navigation. They tried to find their way if it was the first time. And moreover, there are multiple activities such as we go to a shopping mall, we go to the airport terminals, and we also go to the hospital. So the point is, navigation is an ubiquitous activity and we do it on a daily basis. So it's important to solve. The challenges in this field is that generally there are multiple challenges, but we can divide it into two big chunks, which is like the rapid increase of the urban population. The entire infrastructure which we have has been overcrowded, and the buildings which were designed earlier were made for accumulating certain number of people, but with the increase in the number of population, the buildings are under stress. And moreover, with these pandemic situations of COVID, I mean, you have to maintain certain amount of distance between inhabitants. So how do we cope up with that? So that's the challenge number one. And coming up with the next challenge is how the design of the building are getting more creative and artistic. And also with the invent of AI and other tools, the buildings are becoming tall, they're high rises, and they're losing their uniformity. The building looks extremely creative, but it's extremely difficult to remember the building. How can you memorize the building? So generally, earlier buildings were rectangular and square, one floor stack on top of each other, and it was pretty easy to remember that on the left-hand side, this is this, on the right-hand side. But now there is no shape to it, so you cannot build a cognitive map, which we will discuss in few slides. So that brings to the question that how can we design a building that can facilitate the pedestrian movement and human behavior? And this is the key question which I'm trying to ask, and hopefully during the duration of this presentation, I'll try to answer that question. So before moving forward, I will quickly have a brief explanation on what is human wayfinding. So we have been talking about wayfinding, navigations, and locomotion. These are three different terms. Generally, people use them simultaneously, like synonymous, but they mean three different things. So navigation is, let's say if navigation equal to wayfinding plus locomotion. So what it means is navigation is the process where we try to figure out how to solve a problem and then how to act on it. So wayfinding is the decision-making part, and this is what we are involved in. So wayfinding, in short, is the acquisition of information, like as we see here. Someone looks at the sign and gathers some information, so that's like acquiring information in the world, followed by processing and interpretation. So you see from one point, from a start point to the end point, there are three different routes. And then we decide which one to take, and then we act on it. So let's say in this, a person decided to go straight and then take the decision turn. So this is, in short, in a very brief, what human wayfinding means. So here is a small video in a simulated environment where, let's say a person is walking in an indoor environment and it's looking all around. And there are many distractions in the environment. Like you look at the sign, there's shops. If there are people, you will also go and you will get distracted by people. So the idea is that there are multiple factors in the environment which impacts how we navigate. To sum them up, there are two different kinds of knowledge. One is the knowledge in the head, and then there is another knowledge in the world. Knowledge in the head means that if we keep going to a particular environment multiple times, we start remembering it. So we generate a mental representation of the map. Like if I close my eyes and take a pen and a paper, I can actually draw that this location should be here and there. That's the cognitive map. And then there are knowledge in the world, which is like landmarks, signage, crowd flow, and spatial layout. And these all factors are responsible that how do we make a decision. So we will speak on these in detail in the next few slides. And there are other factors like physiological. If my eyesight is weak, I'm unable to see far, then that impacts our decision making as well. Then there are other cultural and the gender biases which happens. Like let's say I came from Asia, so I'm used to walking on the left-hand side, but the people here walks on the right-hand side. So these things have an impact. So the approach which we generally take to solve such kind of a problem is mentioned here. So basically what we do is we conduct experiments with human participants. So on the left-hand side, if you see, there's an experiment platform. So we conduct 3 different kinds of experiment. Either we bring the public to the lab, we give them a particular task and they solve it. And then with the invent of the new technology, we have the immersive VR where we can put them with the HTC headset. So it's more realistic. The idea is that you get a better data and more accurate data. And the third one is crowdsourcing. The crowdsourcing is something which, if you want like thousands of data, so what you do is you create an application, let's say a mobile phone app, and you put it out there and everyone participates on it and you collect the data from them. So that's crowdsourcing. Then what we do is we pick up individual factors. So let's say we have signage, space, memory. So we pick one each at a time. You can pick all together as well, but that will be a very complicated experiment protocol. So let's pick one at a time. So we take signage and then we conduct experiment with it and we see how human beings interact with signage. Then we get some kind of an idea or notion with it, and then we build a computational model. And that model is then used in some form of simulations to create, let's say, a pedestrian movement or a crowd simulation. So this is the overall process. So now, that was the entire approach. So let's break it down and see one at a time what we did. So I will try to highlight few of the things which I did during my PhD and what we completed in last year here in the LOC. So let's start with the human signage interaction model. So what we see here is how can we model the interaction of an occupant with a signage system. So let's move on to this one. So what we see here is on the very top, you see there is a small signage which is mentioned with with green, and then this entire circle which you see is called visual catchment area. This visual catchment area is the location from which you can see the sign. So if you are within the sign, you can so basically the earlier research in this field was that this visual catchment area was like a semi-circle. It wasn't a complete circle. Then the next advancement happened in the research and they made it a complete circle. And then what they did was, if you're inside the circle, the sign is visible. But if you're outside the circle, the sign is not visible. So that's more like a binary which may not be very realistic. So what then we did was that, is there a concept of information gain? So uncertainty, which means lack of information, is a function of a distance and an angle. So if I'm looking at something from a far distance, I have very less confidence about it. So you try to go closer to it and gain more information about it. So this circle and the heat map, the density map which you see here, represents that uncertainty. So if you're at the edge of the circle, which is highlighted by the warmer color, that is red, you see that you have high uncertainties, which means less information. So that will lead you to walk closer to a particular sign. And in that process, you will move closer towards the lighter color, which is green, and then hopefully you will have more confidence, and then you know, okay, so my gate A2 is on the left-hand side, and then you decide and walk towards it. So this entire process is called information gain. So this is a small video which showcases the reactive agent versus the cognitive agent. So here an agent is walking, looking at the sign and going straight. One information which is not visible on the video here is that next below the sign, they mentioned that going straight is 10 minutes and looking at the left-hand side, it's 8 minutes. So the smart agent decides which particular sign to choose from and then decides to take the left-hand side sign and moves in that direction because it's shorter. And these are some simulations which showcase how we interact with sign in occlusion. Okay, so now we modeled how the interaction process of human being with a sign. Now what can we do with it? So that was the fundamental aspect of the research. Now we move on to the application of it. So we developed something called AutoSign. And this is a tool which can be given by designers or to architects who can design the signage system for the building. So we call it AutoSign because it automatically generates the signage system. So in this, what happens is all we need is a floor plan, a 3D model of a building with the origin and the destination paired. That means the entry and the exit point in the building. That's it. And then with that, we can generate all the different signage system which is required. So the key, that's it. This is all we do in this project. But the key part is how do we do it? And to do that, we have to identify the decision point. So let me play a video which highlights that. So I'll forward it a bit. So basically, all these signs which you see are being. So yeah, so let's say this is the top-down view of a floor plan. The first process is that we pre-process. So let's not go into that detail. So now what we do is we extract a decision point. So this particular video is trying to showcase what do we mean by decision point. So if you are at a Y-shaped corridor, you have to decide at a particular point, and that is what we call decision point. So these red points, what you see is the decision point which we compute from the floor plan, and all the blue nodes which you see are the sub goals, which means at this decision point there are multiple options you can take, like go left, right, or behind. So those are highlighted by blue. What we do is that we also provide user intervention. So it's like a designer can play with the system and start selecting that, okay, if this particular decision point is not at the right place, so they can change it. And right now what we see is, so all the red nodes at the extreme proximities are the endpoints and the exit and entry, and we create all kinds of map the path, and then the agent can follow the sign and start walking using that. So this is the user control, where if a particular sign is not at the right place, you can play with it. So a designer has a control and you can change the location of it. So that was the first aspect. So okay, this is good so far. Now how can we improve the system? So now what we did is we tried to optimize the location of the sign. Can we do it automatically without the human intervention? So there are multiple ways to do it. So I won't go into those details. So basically what we do is, so yeah, so we are trying to optimize the location of the sign. So we try to rotate it at the location and see how can the visual catchment area, which we saw in the earlier slides, we can improve the total location. So what we observe is, I want to find. So basically, yeah, this particular example, where a sign is located like that, and the green area highlights the visual catchment area. So you can only see the sign once you're within that green part. So now how can we improve it? So what we do is we make the sign turn a bit, and then the visual catchment area increases, and then a person who is at very far from the sign can still gain information from it. So this is the whole process. Okay, so now we have a static sign. Now we went one step forward, and how can we make it dynamic? So now what we see here is a Cooper Hewitt Museum in USA, and with their permission, we burnt it in simulation, of course. And the idea was, how can we showcase that using an adaptive signage system is better than having a static signage system. So in this, what you see is the signage system on the left. There are multiple. It looks dynamic because it shows the direction. So the best part of it is that there are multiple sensors in the environment. That sensors can send information to each sign, which is the decentralized part, and the sign can decide for itself that should I be a right sign, which is green, or the red sign, which is blocked. You're not supposed to take that. So we did that. We did it with the real human beings and with the agents. So what you see here, a bunch of agents trying to escape the building using the adaptive signage system. And there are two aspects of it. We did the centralized and the decentralized version. The centralized version is that there is one common server. All the sensors which are like in each room sends the signal to that particular server, and the server then decides which sign should be the lit or the green one, or which sign should not be occupied. And then there is the decentralized, that the power of deciding which sign should be on or off is with the sign itself. So what we see here are the bunch of trajectories which an agent took. So using this, we can do all kinds of things. So yeah, that's all we did. And here are the results from the human behavioral data. What we see on the right-hand side is the health score. So if the sign we used was adaptive, we see that the score was slightly higher. The health was better. So less amount of burnt, if you can say that. The damage was done. And also we see that the path length was less. And the time taken to evacuate the building was also less. So thus the hypothesis which we started, that can the dynamic adaptive signage system perform better than the static one? Then yes, we can. It seems to be working. And then we also measured the physiological data of human participant while conducting the study, and we see that the distress factor was less, which is measured, shown on the left hand side. Okay, so we are done with sign. We did 3 different kinds of signs. Let's move on. And then the next factor which influences human beings and their route choice is the space. So if we are in an environment, let's say if there's a Y-shaped corridor, one corridor is large and has a bigger length, then the other corridor is small and thinner. So generally what we human beings do is like we tend to drift towards the wider corridor, which is maybe brighter as well and all those things. So space has a factor which pulls you towards it. I mean, generally when we make a decision, there are multiple factors, but our goal is to break each one of them individually. So right now we are studying space. So in this, what we did is we collected 25 floor plans from the real world, from all parts of the world. And from there, we extracted all the intersections. And then from each intersections, we clustered them, and we found out that there are 5 different kinds of intersections in a floor plan which is generally made. And from those 5, we selected top 10, and that means we have 50 intersections now. And from using those 50 intersections, we conducted a human study. Another factor which I want to mention here is that we can quantify space. So the researchers like Tandy and Benedict in 1967, they created a mathematical formulation called ISOVEST, and they use ISOVEST to quantify space. And ISOVEST has multiple measures. The most important ones are areas, perimeters, and the drift, the occlusivity. So the point is, we use these measures to quantify each intersections. So now using that intersection, if you see this, if I can, this particular decision point here, if you see, we can, using that ISOVEST value and the experiment which we conducted, we can decide what is the probability of taking this corridor, and the third corridor here. So now once we have the probability of taking each corridor, what can we do with it? So there are certain scenarios where we want to guide human beings, more or less indirectly or implicitly nudge them to take this path. And more often, sometimes it is required in hospitals because they want to go towards the help desk faster, or in the airport when everyone has to go through the duty-free just after crossing the immigration because they want to sell more products. So you have certain scenarios, we want to force people to take a particular path. So this kind of implicit behavior or the nudging can be useful in that direction. So after that, I mean, once we have the probability for each corridor, then we ran a optimization algorithm and we try to model each intersection. So the video which you can see right now here is the floor plan, and we are optimizing each intersections and we are changing the shape of it. And this is the 3D view of it. So what we see on the left hand side is that there is a wall present here, and a person, this is the data from a real human being, goes straight when we did not optimize for the space. But on the right hand side, which says GPD, it was, let me play that again. Yeah, so on the right hand side, since the wall was not occluding the right hand side corridor, a person naturally took the right hand side, right corridor, and this convinced us that yes, we can play with the space and we can change the structure of the intersection, and that can implicitly pull someone towards it. So that was the space. And this, okay, so let's move on to the memory part of the human wayfinding. So we all know that landmarks plays a crucial role. For example, if someone wants to tell me a direction that how did you come to this place, someone will use the landmark, if I don't use the GPS, of course, will say that did you see the post office which was in yellow? From there you should take a left turn. So this post office acts like a landmark. And there are, so this is in a bigger scale, but the landmarks can be within a small environment as well, like indoor environment. So the goal is how can we identify these landmarks? So this work dedicates itself to identifying such landmarks. And the landmarks have multiple features such as visual saliency, spatial saliency, and subjective saliency. So visual saliency is like how the landmarks look and feel. The spatial saliency is where the landmark is located with respect to the decision points. And the subjective saliency is like, I will use the landmark which I'm more familiar with. For example, I drink my coffee at Starbucks, let's say. So if I see a Starbucks, I will tend to remember it because that's my subjective landmark. It's easy to recall. So that's why these are the three factors. And what we hypothesized was that these three factors are, along with the low-level features, are hierarchical in nature, and that is the perception model found generally in human brains. So doing that, we identified the landmarks, and the example which you see here is the figure A has the 5 decision points. We have highlighted 3 decision points, and all the landmarks which have been identified by human experiments and via our computational formulation is shown here. So in general, what we have found that our method can predict 79% of the time the landmark which a real human selected. And how did we make the real human select the landmark? We used the eye tracking data. So we gave them the HTC, the headset, and then they asked them to navigate from one point to another. And from there onwards, we extracted the landmark from the eye tracking data due to the fixation point and our formulation. And then we found out that there is 79% of the time we can predict what landmark they choose. So this feature can be very helpful for let's say a Google map. I mean, people, I heard that some of my friends in Google mentioned this, that they are working on this way of navigation now. Instead of giving a metric distance of going 20 meters forward and take a left from there, they're trying to identify these landmarks and making it more intuitive. So they will give directions that do you see a red building in front, take a right from there. So this is what this particular method can move towards. Okay, so we spoke a lot about landmark, and the use of landmark is to build the memory. And in memory, I mean cognitive map. So in here, there are 2 important parts. The first is how do we plan the path, and the second is the spatial memory distortion. To move on, I will quickly show this map and ask a particular question. So this is the map of Germany. And if I ask everyone here, I mean, please participate if you know it, the distance, the direction from Dessau, which is in the state of Saxony, to Wittenberg, which is in Brandenburg, what will be the direction you will see? The point which I am trying to highlight here is that there is a distortion in each and everyone's mind, and that comes from a higher level cluster. So if anyone knows where Dessau and Wittenberg is, can you tell me? Is it on the northern side, northeast, northwest, south? Okay, so let me move on. Northeast, right? Okay, so good, and thank you for that, because this is exactly what the distortion leads to. So the point is, Saxony right here is located on the left-hand side of Brandenburg. So immediately anything which is in Saxony will be like, okay, from here we have to go towards the east or the northeast. So this Saxony acts like a higher level category. It's a cluster which biases my decision that I'm thinking now at that higher level. But the whole point is, if I showcase where each of them is, it is like this. So it's not northeast, it's not northwest. So the concept, the idea, the notion of northeast came due to the distortion, and that distortion came because in my mind, I know that Saxony is on the left-hand side. So it should be always on the right hand side. So if someone wants to make a decision, let's say if I'm driving, trying to reach from Dessau to Wittenberg, probably with that distortion will push me from towards, I'll take a turn towards Brandenburg and then move up. So these path planning decisions, if you make it locally, also impacts that you can go to a place from 3-4 different ways, but which one do you actually take depends on these distortion, and this distortion occurs of your involvement with or your interaction with the environment. So if you keep taking left to reach a particular goal, you will always take the left. So this is what I wanted to highlight here, that how spatial memory distortion is important for path planning. So all the previous work which they did was, we know all these simple path planning algorithms like A star, D star, and what they do is they find you the shortest path. But this is not how we work. We human beings are filled with errors, and we need to quantify these uncertainty to create a, let's say, the correct simulation results. So to do that, we need to include these distortion. So that's the distortion part of it, and I will quickly, I think I have 10 minutes. I can quickly describe what else we did. So the previous researcher, I think Werner, they came up with the concept of find-to-coast model. So find-to-coast path planning model means that if I have to go from point A to point B, I do a fine level path planning near A. So let me take an example. So if I want to go from Munich to Paris, what I do is I'm focused more on making a path, a very accurate path. How at this, let's say this particular location, how can I find a path from here to the nearest highway? So I'm focused more on the fine level details. I don't bother about what is going to happen, let's say if I reach the border of Munich. So that's the coast level. So what find-to-coast model means is that I plan my path at a fine level at a location nearby to me. So this is what is shown in this hierarchical maps. So if this is Munich and that is Paris, let's assume, we plan detailed here, and then at this location we do not plan at that location. We go here, the cluster which is found in our brain, and we plan here. So we plan this path, and then we start breaking it down at a coastal level. So this is the find-to-coast model which was proposed earlier. What we did was to add the spatial memory distortion to this model, so that now we can also incorporate the mistakes which humans do. So, and again, the whole formulation was that we perform experiments. So that's why you see a virtual reality setup here. We bring in people, we make them walk from left to west, left to right, and from right to left, and then we observe. So exploration pattern also plays a role. If you are seeing, so basically the thing which you see earlier is what you remember the most. It's counterintuitive, because you will say the last thing which I see is the thing which should be fresher in my mind, because that's what is the last one. So it should be very fresh, but that's not how it happens. What we observe is the first thing which we see is more prominent in our brain, and those impacts our decision making. So this is, we use these to build a cognitive map. So I won't go in detail about how we do that. So we are done with this. So basically this experiment was conducted, okay, never mind. Okay, so this is the last, this is the work which we did here in LOC with Professor Bowman and Jimmy. And this is the work which involved reinforcement learning. And what we did in this is to create an adaptive path planning system. So before going to that, I will quickly like to explain a bit of what reinforcement learning is. So let's say, take an example of a young child, a toddler wants to learn how to walk. How does a child learns to walk? It's a trial and error thing. So what you see is that a child makes an action, which is like put the left arm forward, the crawling motion, that's an action. The state is, let's say the child is within a room. So that room is the state, the environment. And the reward the child gets can be two different kinds, which is like one intrinsic reward and the other extrinsic. The intrinsic reward is that if the child perceives that it is getting closer to, let's say, a candy. So that's the reward in itself. And the extrinsic reward is when the child reaches the candy, then it actually gets the candy. So that's the extrinsic reward. So the reinforcement learning method is this loop. And everyone is going through this loop all throughout their life cycle. So if I'm presenting right now here, I'm making certain mistakes during my presentation. And that mistake is acting as some kind of a reward prediction error, which is teaching me how to present in future better. So this entire cycle of learning from trial and error is a simple definition of reinforcement learning. And reinforcement learning is, of course, highly derived from how we human beings live and learn things in the world. So now once that is done, so that is the what part of reinforcement learning. What is reinforcement learning? Now the big question is why? We have already been using the computational mechanism, doing the psychology experiments and conducting and creating the formulation. Then why do we need to have reinforcement learning? So the idea is recently with the advancement of tools like functional imaging, fMRI data, and the physiological data, we have started to notice the functionality which happens in our brain, which is the neural substrates. Some of them are following the principle of reinforcement learning. So by that what I mean is, so there was an experiment conducted with monkey. Some people conducted an experiment with monkey, and what they did was they trained the monkey to press a button, and every time they press the button, the monkey, juice comes out. So monkey started to keep pressing it, and they measured the dopamine. So dopamine is some kind of, let's say, a spike in your brain that helps you, so it makes you more curious in a very simple term. So we use dopamine to do anything in our life. So if I am presenting something, my dopamine level might be slightly higher right now. If you drink coffee, it increases, chocolates and something like that. So the monkey learned how to keep pressing the button to get more reward from it. And every time when the researchers measured the dopamine level, it kept on rising till the level where monkey actually understood the concept that pressing the button will give the monkey the reward. So after that, the dopamine level did not rise. This concept is derived from, in reinforcement learning, this concept is temporal difference, the reward prediction error. This is what, after finding from the neural substrates, we identified that they match. So that is the question why. It's good. We don't know what AGI, the artificial general intelligence, will lead us to, but this is the closest thing which can lead us to. So it's worth exploring reinforcement learning to model human decision making. So with that out of the picture, I will very quickly describe what we did here. So in this, the goal was how can we model our path. So the adaptive path planning. So we have multiple neurons in our brain which we use to compute. It acts like a GPS. So we have grid cells in our brain, place cells, and border cells. Grid cells in our brain is as a GPS, and it helps us to identify the direction between 2 points and the distance between those 2 locations. Place cells is right now telling me that I am localized at this location with respect to the room. So these are, we take it for granted, but there are a lot of things going on which happens. And then there are boundary vector cells, like if I go close to the wall, those cells will give me the reception that I'm actually close to the boundary. So you should not go closer. So we use all these things to make an agent learn. And there, in path planning, there are 2 different ways. So we propose that human beings generally follow a vector-based navigation and a topological navigation. By vector-based navigation, what I mean is a straight line path. So if I need to go from this point to Casimir, I will generally do a straight line path. But if I have to go to, let's say, outside the room, I cannot walk straight because there are walls, and so I have to find the door. And that door, it acts like a sub-goal. So I find my straight line path from here to that goal as a straight line, and then I plan my next move. So the idea of identifying sub-goal is very important. So we use another concept which is found in human brain called successor representation to identify these sub-goals. But let's not go in detail there, and I will quickly show the experiments what we did. So these are the results. So what you notice is that there are 2 different sub-goals. One on the left-hand side, this one, is the earlier method which they identify the center of the cluster. what we identified was the subbulb should be here rather than at the center. And we showcase that it produces better results. And in this, what we are seeing is how the black is the sub-goal, and this sub-goal is constantly changing. So if the wall is blocked, how the green agent can navigate to the yellow. Yellow is the destination where the agent wants to go. And basically, yeah, so let me move forward a bit. Yeah, so another important aspect of human being is that we know how to take a detour. If a particular path to my destination is blocked, I know that I can take a detour, like if the barrier is added. And the same thing is with the shortcuts. So right now what you see is that the agent has to take a long path to go to the yellow. But then there will be, let's say if I remove this barrier, which is highlighted in the video, I remove it. What happens? Will my agent act human-like? It will, because if it is open, I will generally take a shortcut and go straight towards it. And this is what we showcase, that if we model using the neural substrates and formulate those neurons, these behaviors automatically come out of it. So what we are trying to showcase here is, I mean, these behaviors are very easy to do. You just hardcode these steps. But the point is, we don't want to do that. We want to showcase that modeling at the lowest level can result to such behavior, which we witness using behavioral data. So in this way, we can convince that exploring RL makes more sense. And this is just to showcase how our method works in a complicated and a large environment, so this particular slide. So I think with that, I would like to thank you all for listening. And if you have any questions, I'll be happy to answer.
Are there any questions? Too many. Then go for the first one. Yes.
Thank you. Thank you for the excellent talk. In the first part of your presentation, you presented methods to automatically create signposts in buildings. Have you also considered, because not every time in every building you will probably be able to put an additional sign at the ceiling, because maybe the ceiling is even too low. So have you thought also about how to reuse the existing space, the wall space, etc., to place these kind of signposts?
So we have not conducted an experiment to actually answer that question, but yes, this question can be answered by the space. So like, since we do not have more location for hanging the sign, it also increases the clutter in the environment, which you don't want. So what you do is you try to work with the space. So let's say if I have a 3D model of that building, and there is a particular wall which, if possible, I can make it a smaller, or if there is a flower pot right there, I can remove it. So the whole idea is, can we use some kind of space to induce the feature which the new sign should be providing? So yes, that is possible. Or we can also add some kind of a landmark around that place, so that we will remember that when we see the landmark, even from far, that okay, I know from there I have to take a left. So we can do such stuff, yes.
Okay. Just one extension, maybe because when we think about having BIM models for maybe large new buildings that are being planned, is there then also something in reach that, for example, you can make an assessment how navigable the building will be? So would there be also something like a key performance indicator to tell, okay, that building is a nightmare because there are no landmarks, a lot of symmetry and something like that? Is that something that you can also, would be able to derive and process?
Yeah, definitely. So that's a very good question, and the whole point is that we are reaching towards it. So we can derive it in many different ways. So one is like the path length, the time taken to go from one point to the other. The more realistic way which I'm interested in is that at each location, let's say if we break the entire environment into grids. So at each location, which is 1 × 1 meter grid, like a tile, what is the uncertainty at that particular location to go from this point to any other point? And then we can cumulative add them up, and then we can produce like a density or a heat map and showcase that how navigable the place is. So yes, it is very easy to quantify, yes.
Any more questions? If not, thank you very much, Rohit, for your talk. And maybe one thing to mention is that due to Frau Obermeyer's donations, we could carry out this finance this postdoc scholarship. One of three scholarships from Leonhard Obermeyer Center. Vielen Dank, Frau Obermeyer, für Ihre großzügige Spende, die diese Forschung ermöglicht.
Thank you.
And our next speaker is Christos. He's the managing director of the venture lab Built Environment, and he will give an overview about scaling innovations in the built environment.
Thank you very much, Casimir. Thank you very much for your attention today, and happy to be here. I'm presenting the venture lab Built Environment, which Professor BORRMANN touched this morning already with what we are approaching. It's about bringing entrepreneurship closer to research, or research closer to innovation and entrepreneurship, and to scale on a broader perspective. The great research you have done so far, we have seen this morning, and to push a bit the BE industry, the built environment industry, in the innovation and entrepreneurship direction. And in this greater perspective, if you look at Europe regarding the venture capital and the funding of new startups and entrepreneurial endeavors, you see that we are doing well, but compared to the North American area or the Asian area, there's still some potential to step up in that direction. And the mission and vision is to become Europe's leading tech hub for tech sovereignty, and to provide an excellence in entrepreneurship and research in Europe, and also create a greater ecosystem as we already have right now. And the TUM Venture Labs are a joint initiative from the TUM and the Unternehmertum, and describe somehow a unique blend of excellence. We have on the one side, as here with the Leonhard Obermeyer Center and the TUM School of Engineering and Design, great potential of advanced research and also initiatives, and also with the Georg Nemetschek Institute for Artificial Intelligence and the Built World, we will exceed or excel in that field even more. And on the other side, we have the Unternehmertum, which is currently the most successful incubator in Europe. And if we combine the research excellence and the entrepreneurial support excellence, there should be also some more promising startups and entrepreneurial endeavors to come. And we are very happy that we also got our first sponsor and supporter on board, which is the Nemetschek Group. So at this moment, another warm thank you to the Nemetschek Group for sponsoring this initiative to scale innovations in the BE industry. And it's also directed to researchers. So we want to support, to help researchers to think about an application of their great findings in industry, in economic terms, and to take what we have seen this morning, for example, with BIM in factories. How could an entrepreneurial application look like, or an economic application look like? And maybe for the researchers to offer an opportunity to found their own company with an entrepreneurial spirit. Then we do venturing, means supporting with coaching, with dedicated classes and programs to help the people on their way to a successful company. We provide a network of researchers to support with their opinion of industry, to support with their opinion, and also maybe to finance them. And we provide an infrastructure, meaning spaces to work and also technical facilities to use and design factories to use. Our startup pipeline is now starting. We are already in contact with several companies and startups, which we then coordinate and coach. Some of them got into our direct support. Some of them we keep in touch to track also their development and help them if there is a need for that. And we want to become as said in the beginning, a platform for exchange of mutual support to help young researchers, entrepreneurs to scale their important impact. And very young, the BORRMANN team is also supported by us, a student initiative, which won the BORRMANN competition this year, which is very, we are very happy that we are one of the supporters. Then we have another startup, which is rethinking parking in inner city areas with vertical parking towers and trying to create mobility hubs. Then we have Plan for Better, which is helping communities to plan inner city routes and pedestrian routes and optimize their wayfinding through the city. They currently received, or they recently received, an innovation prize from the city of Munich. And since 2 days ago, they received another innovation prize award from the Bitkom. And now we also have a contact to Einwert, which is digitizing the valuation of real estate. And last slide, from our board or the team, we have 2 academic directors, one Katrin Dörfler from Digital Fabrication, then as mentioned, Konrad Nübel with his expertise, then also Frank Petzold is supporting us as entrepreneurial ambassador for the TUM area in architecture. Tobias Förtsch is managing director, and me, and then from Unternehmertum side, also Manuel Götzendorfer. And above all, these venture labs wouldn't have been possible without the strong support by Professor Gehlen and Professor Hild, who initially pushed that we had this venture lab. And of course, now with Nemetschek Group, we are ready to take off for the future. Thank you very much.
Thank you very much. This was our first session. We will have lunch prepared in the back. We will have 1 hour lunch break. So the live stream will stop now and be continued in 1 hour. And thank you for coming, and I hope you can enjoy lunch. I would like to welcome our next speaker, Dr. Ludwig HOEGNER, from the chair of Photogrammetry and remote sensing, also one of the LOC chairs. And he will give a presentation now about extraction of LOD3 objects for 3D models from point clouds. So warm applause and thanks, Ludwig.
Yeah, thanks for the introduction. I will talk a little bit about some things that I have done, and especially one of our doctoral candidates, Olaf Wysotsky, has done in the last few months. So the idea is what data sources do we use for 3D model enrichment, and then I will show 2 examples, one image-based geometry extraction and point cloud-based geometry extraction, and then I will give a short outlook what will be our next works. So our data sources are different kind of point clouds and images. In that case, we can see a fully automatically generated dense 3D point cloud of a kindergarten in München-Mosach. So that's one possible data source that we can have. Then we can have something like this. That's airborne laser scanning in an oblique view to record the facades. Or we have a data set like this, generated together with a Fraunhofer IOSB from a mobile mapping laser scanning system. And on these systems, not only laser scanners can be mounted, but also camera systems. In our example case, a thermal infrared camera. And here one can already see a first processing step, the automatic rough point cloud labeling that directly tells us, okay, which points belong to buildings and facades, which points are cars, vegetation, ground, or some street objects. So and this would be now a thermal infrared image sequence where we record also the university buildings, and one can see here the main entrance before the renovation, and here recordings additional from a static thermal infrared camera. And the interesting question is, how can we now
come from a LOD2 to LOD3 building model, and one idea is, of course, adding windows is always a good thing, and in our case we can add also special windows, namely windows that are not visible anymore. They have been closed years ago, and with thermal infrared cameras it's quite often possible to also see those old structures and add these structures. In the end, what has to be done? We have to co-register an image sequence and a model, and from this co-registration we derive then parameters to project the model into the image sequence, and from this we then generate textures like this, so that's fully automatically generated texture. And this part of the building was not visible in any of the images, so here it stays just black. And here a view from the whole ETHZ, from the automatic texturing generation. And if we have this, then we can use simple image processing techniques or simple image-based neural networks to detect objects in these facade textures. We can detect, for example, possible leakages, and we can detect here the windows. And that's of special interest because windows are also disturbing objects in case of the calculating temperatures of facades, and so we mark these windows and remove them. And one can see that especially here with these complex window structures, there are still some problems in the correct detection, but for standard windows, like we can see them in these two rows, the detection is more or less 100%, and if one of these images is missing, then we are using given grammars like a Gestalt system to find missing windows inside these detections. And as these textures have texture coordinates on a facade, it's possible then to transfer the extracted objects into the building model, and by this we can enrich then the models. So this is quite good working. If we have simple basic geometric objects like corners or rectangles for windows, we can use grammars for the identification, or we can use a set of training images, for example, for neural networks, how do windows classically look like, and then train this for supervised classifications. But there are quite limitations. With this, we can only detect structures in the estimated facade plane. So if objects are outside the plane, then their projection in the texture is wrong, and still any kind of reconstruction only is in texture coordinates of this model. And of course, we can miss objects by this. And we cannot handle objects that do not follow simple geometries, like, for example, these faculty symbols that are on the facades. They are simply missed with these techniques. So another way that we investigate is extracting geometry directly from point clouds. And here I want to show what Olaf Wysotsky has done in the last few months. We can assume that we have different types of laser point clouds. Here one can see again the aerial laser point cloud, where every window can be seen only as a very small gap in the point cloud. And from this it's possible to also derive the windows, or it's possible to refine the model, in this case as an example, the underpasses. So classical LOD2 models always start with the buildings from the ground, so these underpasses are not part in these models, and the idea is to automatically detect such underpasses for the refinement of the models. So the general idea is that we're transferring the point cloud. We have millions of points into a voxel space, and for this voxel space we detect which voxels must be free, so unoccupied, because we can see some points behind that. We can see where can we see points in voxels that are behind the facade that we expected, so where we said, oh, there shouldn't be any point because there is a facade before. And from that, and the green ones, these are points that fit to the facade. So we can say, okay, these are points that lie close enough to the facade so that within the accuracy of our measurements, they say, okay, the facade really is there. And here, for example, there is such an underpass that's not given in the original model. There is a conflict because we assume that the ray should intersect the building here, so there should be the 3D point, or the voxel should be occupied here. But here the voxel from the point cloud is free, and we can see points here inside, and if we back project the rays to our sensor, we can directly say in which part of the building model there is a conflict, because the model geometry doesn't fit the real geometry that we measure with the laser scanning system. And we can then group this together, for example, for the facade windows. The idea is we can assume where should be the facade plane. We have a given model plane, and we have a big set of points that belong to that plane. And from that, we can, in a first step, adjust where the plane level should be, and then we can see, okay, where are gaps in that plane, where there are no points, and on the other hand, where are points from the viewing position of the scanner scene that are behind the plane. And then there must be gaps or holes inside the facade, in this case, a reconstruction for the windows. And if we see at the facade from the side, we can see that there are points behind the facade planes, and this then indicates that there is not an occlusion from outside, but that there really is a hole inside the estimated facade plane. We can then group these detected holes. For example, we can say, okay, they should group in rows and columns, and there should be a regular window structure. And here, these fields here indicate the possibility, the probability that there is a hole in the facade plane to be connected, and from that we can then reconstruct a regular structure. This, for example, is an enrichment of an LOD2 model by the extracted window elements. And here one can see that still the underpasses are not modeled here. That's only the window extraction. That's now from the mobile mapping system, a fully automatic detection of the Adress. Here facade planes and windows are fully automatically detected. And now the last example, underpasses. Here we have projected the LOD2 model to the street here, and one can see that here this is more or less a massive building block. And if you look at this in the mobile mapping point cloud, we can clearly see here the underpass, and that's already a classification of the point cloud where we again here have building and street and cars. So there seems to be a mismatch between both of them. Or here, that's the underpass to the inner yard of the university. We can clearly see it in the point cloud, but it's not given at all in the 3D building model. So we can generate here a conflict detection where green are correct points, and here we can see the points that are at the non-estimated location here. And if we do this with a set of underpasses around the university, we can, for example, generate here a space where we see, okay, that should be the clearance space that must be free to see the points inside the inner yard. So we have now to cut out that part of the original building model here, which can be modeled, for example, in that way. Here we cut out now the parts that were identified as there must be holes in the facade plane to be able to see the points that are in the inner yard. And this then is added to the modeling. What would be the next steps? Here again, one can see one part of the building model with labels. Here we can see that we have many small structures, in that case manually labeled. Here are the shields with the faculty symbols. Here are the windows. Here's some overhangs in between. And the next step will be to extend the method to also distinguish different levels in facade planes. So far, we still assume a facade plane to be one plane in one level. And now the idea is to extend this to split facades in different segments so that we are also able to model these different facade planes in the different storages or levels of a building. So this would be the next stairs. And then thank you for your attention. And I think we have time for questions if there are.
Are there some questions? Yes.
Thank you very much for the nice presentation. Regarding the underpass, I think that works pretty nicely. And however, when of course looking at your reconstructed windows, there's a lot of deviations from reality so far. Mm-hmm. Have you also had a look already at maybe other methods, for example, using deep learning or something to identify the windows, which might end up with a more correct representation of that?
Mm-hmm. So what we want to do is to combine the laser scanning point cloud with photogrammetric data, so with the image data. There we want to start a project, but that's what started so far. So in the end, more or less, these laser point cloud-based detections should be more or less the seed points to tell in a second step the photogrammetry where a window is, what more or less the size of the window should be, and the photogrammetry should then try to cut out the refined windows. And for that, we try to make a real fusion between the laser point cloud and the stereo camera system. But that's still work in the future that we hope to be able to start maybe December or January. Because of course, simply from the way how dense the laser scanner, the airborne anyhow, and also the terrestrial laser scanner, the density it catches the points of the points that really are the corners of the windows is not really exact. That's why in the fully automatic reconstructions, we get quite good the number of windows and their location, but the size is still quite rough. That's much better if we include photogrammetry and then can use this also as input for a neural network that simply has learned how windows look like in facade textures.
Yeah, please.
You were talking about conflicts between the point cloud and the model that you already have. Mm-hmm. How big does the conflict area or volume have to be so that you consider it? And do you also consider additions to the model or just areas to cut out?
Mm-hmm. So if we have a look at, let's see, here there are only very few points that indicate that there is a conflict. So in the end, we can decide in a threshold for which points we need to say, okay, there is a real conflict. In the end, it depends on the number of points and how big we take the voxels for the reconstruction. From the voxel size, more or less, we define in a voxel space which voxel shows a conflict because it should be occupied by the model but is free. So more or less, our resolution depends on the voxel size. And that's what we use as a basis. And this is a simple conflict analysis of the projection rays that we use for that. And that's why one of the next steps, this facade element refinement, is that also the given facades in LOD2 have limited accuracy. So the facade plane itself is not centimeter accurate in the model. That's why that's the next step to refine also this, to be able to put the facade itself at the really correct position within an accuracy of a centimeter, then split it into sub-facades to have also their correct orientation, and then put in all the elements that we have, windows, this vacuity shields, and so on.
Okay, maybe one last question behind you.
Thank you for your presentation. The question that may lead a little bit far away from what you're actually doing, but my question is activities to detect materials by photogrammic activities or maybe hyperspectral questions.
In principle, the procedure would be the same. In hyperspectral sensors, we would have a bigger pixel, or the ground sampling distance would be worse, so we would not see so many geometric details. On the other hand, the projection process is the same, and one can see this, for example, for the thermal structures. Here also the ground sampling distance is quite low compared to the ground sampling distance that we have in RGB images, and there more or less the methods are working the exactly same way. We are also able to reconstruct 3 point clouds from that, but then the point density is much lower. So of course this would be working with hyperspectral data as well. I would then prefer to have a hyperspectral data that can be recorded with a plane array, so to keep time gaps between the different channels smaller, because one main problem in the fusion process is always having dynamic objects in the scene. And to avoid this, it would be good to have then focal plane arrays with different filters for different channels.
Okay, so thank you very much. I fear we're running out of time, so thank you again, Ludwig, for your great presentation. And our next speaker is Andreas DONAUBAUER, also a postdoc from the chair of Geoinformatics, an LOC chair, and he's giving a talk about the digital twin of Munich and its siblings.
Thanks very much for the introduction, ladies and gentlemen. I will talk about the digital twin of Munich, and you might remember from André's talk this morning that Technical University of Munich is consulting the city of Munich in building a digital twin. So there are two major digital twin projects running in the city. One is called Digital Twin Munich, the other one is called Connected Urban Twins. And this project is also together with the cities of Hamburg and Leipzig. So I will talk about the digital twin of Munich and its siblings. And my talk will have two parts. The first one is concentrating on the digital twin, and the second part is concentrating on the siblings. So how does the digital twin of Munich look like? This is a slide from the city which should explain what the plans of the city are. They want to have a very accurate and a very up-to-date digital representation of the real city, which consists of 3D geospatial data, of real-time data, and also of thematic data, which is distributed around all the departments of the city. What do they want to do with it? They want to try out so-called what-if scenarios. So they want to analyze this data, and they want to simulate scenarios for future development. What you see here is the area around Sendlinger Tor, so Sonnenstraße. And what you see here is really the level of detail, the granularity you can expect from this digital twin Munich for the whole city. So there has already been a mobile mapping campaign that created very dense point clouds. And out of these point clouds, the city wants to contract some companies who create these detailed street space models of Munich. And this is really new, because if you think of 3D city models in other cities, then they mainly consist of buildings. And Munich, in this digital twin, concentrates on the street space. So then what happens after these what-if scenarios have been carried out? Then, of course, an optimal solution for some task should be found, and then the real city should be changed. And then, of course, the digital representation of the city must change accordingly. But in order to carry out these what-if scenarios, the digital representation must also be changed beforehand. And that's what I will talk about later. These are current use cases where this digital twin is really used in the city of Munich. Also a slide from the city. So they use it, for example, in the security domain, where they try to find areas that are vulnerable to terrorist attacks, and they want to find the optimal places for these barriers you see here. Or they are doing climate and environment protection analysis. For example, they are coupling traffic simulation with the simulation of noise dispersion or of air pollution. Then, and this is also a major point, I said it's concentrated also on the street space model, and that's why these applications come into play: future-oriented mobility. The street space model that will exist is very much oriented at a standard that is used in the automotive industry. The standard is called Open Drive, and it's used by the car manufacturers for testing their vehicles. And yeah, and then you see public participation is also a use case. And yeah, in the lower left corner, integrated city development. That's what it's all about. It's about simulating the impact of changes in the city from the viewpoint of different domains. So yeah, this is the basic conception of the city, how the city sees the technical perspective on the digital twin. The city says it's not a monolithic system, it's open, and the so-called urban data platform Munich serves as the basis for data distribution, and this should also be based on open standards, interlinking existing systems and data platforms. So this is very much in line with a concept we developed in some European projects, and there it was about data management in smart city projects. And what we see on this figure seems to be quite straightforward, but it was really hard work also with city districts around Europe to find this out. So we said there are all the different actors in such a project, like citizens, municipality, utility service providers, and so on. They all want to achieve different things. They all have data. They all want to use data. And then there is data around the city in different domains. We can say that there will always be a virtual district or city model, which could consist of a virtual 3D city model, a network model, and also, of course, of building information models. Then there is a lot of static domain data that can be connected with the digital representations of the physical objects in the city. And then, of course, there's more and more IoT and real-time data from remote sensing, but also from sensors which are installed in the city. And then, yeah, the data is worthless if you do not analyze it. So there are lots of simulators and analysis tools like flood simulation, solar potential analysis, pedestrian flow simulation, and so on. And the actors do not directly use this raw data or the tools. They want to use these by using their specific applications. And the digital twin of the city would then be all the right-hand side, so an aggregation of all the digital information which exists for physical objects in the city. And you might expect that this is very heterogeneous, that it's an illusion to bring all this data into a common platform. And that's why we say here in the middle, this research registry, so a catalog of all the information resources, is a core component of this smart district data infrastructure, and then also of the digital twin. So far, the digital twin. Now the second part of my talk, what are siblings of the digital twin and why do we need them? One might think one definition of a sibling could be that, of course, the city builds their digital twin of the city, but also anybody else could build a digital twin of the city. So are these the siblings? No, not what we think about a sibling. I will explain on the next slides what we think. And I will motivate this by this not quite so fictitious example use case of the digital twin Munich. The city wants to improve mobility, so this means reducing car traffic, extra spaces for bicycles. We know all these pop-up bicycle lanes and so on. And these changes, in order to optimize them, should be evaluated regarding their impact by different analysis and simulation tools from different domains. So for example, a traffic simulation would estimate the current traffic flows, an air quality assessment using pollutant dispersion simulation, a noise dispersion simulation. So this goes also in the economic side. For example, if you close lanes for traffic, what is the effect on shops that are at these lines? So you could imagine any kind of impact. So if we look at these analysis tools a little bit deeper, then we find that the system architecture can look like this here on the right-hand side. We have input formats that where these applications consume the data. There are so-called ETL tools, extract, transform, load, that transform the data so that this data complies to the data model of this application. And then there are several functionalities for using the data. If we have this digital twin, then of course this data can be used directly from the digital twin, again using these ETL processes to transform it. But the digital twin represents the real world, and we want to do simulations on a future state of the city. And so all these applications, if you take a traffic simulation application, for example, they have their own editors for scenario generation. And in the end, the result could, of course, also enrich the digital twin. But if you do these what-if scenarios, they are defined inside these applications and are stored there. So if we want to look from different perspectives, from different domains on the same scenario, then we have a problem because these scenarios are not connected, are unsynchronized. Changes of the digital model made in a specific application, traffic simulation, are not effective in a second application and vice versa. So there is no definition of an urban development scenario that is independent of the application in such a setting. And now our idea of the siblings come in, and we also call it the triplets of the digital twin. And our idea is, instead of generating the scenarios within the realm of single applications, we want to modify the digital twin in such a way that it reflects all changes resulting from playing a scenario. So the same modified data is then fed into the various applications and analytical tools. But of course, we're not allowed to change the digital twin, because this should always reflect the current state of the city. And so our solution is to create clones of data sets that the digital twin consists of, and the aggregation of these data sets will then be our digital triplets. But of course, we cannot clone all the data. We only want to clone the data we want to change for a specific scenario. The other data is used as it is. And I cannot go into detail, I think, in this slide because of time. But the main point is that the what-if scenarios are defined outside the application, and all applications work with the same scenario. So a multidisciplinary view on the same what-if scenario is possible. There are, of course, a number of challenges I address on this slide. We're working on these challenges, but I cannot present you the results we found. And as a summary, I could say that the digital twin of a city is a common data environment for all these applications. The smart district data infrastructure can be used to realize such a digital twin, and the digital triplets are clones of specific subsets of a digital twin. Thank you.
Maybe we can have a quick question if there is any from the audience. If not, thank you very much for your presentation. We will continue with our next speaker, Dr. Thorsten Jelinek from the Digital Platform Governance GmbH. He will talk about federated platforms for digital sovereignty and governance.
Thank you, lovely. It's a great pleasure to speak today here in this prestigious LOC. And I have to say, I was pretty much impressed about the work of the LOC's PhD students on the one hand, but I was equally impressed by Professor Bohrmann that you can recite the output, what they delivered actually. So I'm a software engineer on the one hand, but my PhD is in social science. And I can tell you, after the first year, my supervisor would not know anymore what I was working on in the social science. So I'm really happy to be amongst engineers, actually. We've seen great technologies, and I want to shift the attention to governance. So the G20 infrastructure hub said one of the biggest obstacles of efficient, sustainable, human-centered infrastructure is a challenge of governance as opposed to a challenge of only technology. That means actually all these great technologies, in a way, we've seen in silos. So governance and the idea of federated platforms might be an option or might be a possibility actually to bring those technologies together. And that is the presentation about shared data spaces and federated data spaces. These are the emerging themes which is associated with Gaia X, but also with other initiatives in the United States. We got intrigued by the challenge of digital governance or the governance in infrastructure, which led us to the concept of federation. So let's quickly look into the problem or the challenge. These are the value chain moments in infrastructure, and we observe that they are pretty siloed and pretty fragmented, and that fragmentation prevents a certain change which is necessary, and you have at least 3 areas here. The direct challenge, is the project delays, overruns, etc. Then you have more aggregated challenges. You have huge investment gaps or infrastructure gaps or lacking pipelines to fill those gaps. And then on the top, you see the global challenges. One is decarbonization. So if you deal with fragmented and siloed infrastructure operations and projects, this pretty much delays or is inertia against those laudable goals. But on the bottom, those silos actually are pretty efficient, which you can say, well, that's the inertia, so I don't want to change. So my silo is great. So I think that's the challenge we were looking at. And digitalization, obviously, is one of the issues. And we saw a lot of digital technologies, but in fact, the infrastructure industry is behind. And one maybe measure to see how it is behind is the share of AI jobs across all those sectors. And unfortunately, on the bottom is construction. That means the AI talents are hardly entering the infrastructure or construction sector. And it's not surprising that the information technologies has most of the AI talents. So I think that's an obstacle looking forward that AI, knowledge graphs, etc. There's a lot of efficiency potential. Yes, we saw great presentations, and the infrastructure hub, the G20, has reviewed those technologies, how they're used. But they're used in silos still. They use the optimized silos, and be it product transformation, delivery transformation, or technology optimization within the technology silo, for example. But we don't see an attempt to build more of the data sharing economy within the infrastructure industry. If you take as a comparison the Industry 4.0, the flagship industry, manufacturing in Germany or in Europe itself, we're already entering the second wave of Industry 4.0, where the next 10 years are determined by machine learning, where machine learning learns from those industrial data, machine understanding of data, and the practical use of that. So actually the industry is really moving quickly into what they call into zero-error production and self-regulation. That images is from the FKI Germany. So what's the opportunity? So it's a pretty maybe alarming in a way, but not really. I think we believe it's an opportunity that, in fact, the idea of combining the infrastructure governance, or the construction build governance, then a ICT governance can be kind of mediated through this notion of digital federation platform or data sovereignty, that you start sharing data, but you don't lose the ownership of that data. That's the old platform model that you give your data, they're gone, basically. You're locked into a hyperscaler, and the infrastructure industry is actually also pretty much afraid of it, that the data are lost, basically, so they don't want to share it. But it's not just a company, it's a municipal, a city. They don't want to share. They don't want to share the digital twin data easily because of the limitations of how do I share it securely. It's not just an infrastructure problem, it's let's say also a German problem. This goes to cloud computing, and the uptake is pretty low in Germany, and of course also Europe lacks of these hyperscalers. So the European Union has recognized that. Also, of course, Germany has the German government has recognized that, and starting building common European data spaces. Unfortunately, there's no infrastructure data space yet. There's smart cities activities, but we don't see that smart city activity has a different angle than the complexity of infrastructure itself and the value chain of infrastructure. So we don't see it here. The International Data Space Association has this data space radar, and we from DPG, a startup, and collaborating with the chair of the construction process management of TUM, we hope that at one point we will be located somewhere there, or someone. It would be already a big achievement that there is an open data space or trusted data space for infrastructure. Maybe it goes back to the claim that infrastructure should have its own ministry. Maybe that's a little bit symbolic of the issue we're structurally facing. Of course, we are as a member of Gaia X, we are inspired by Gaia X, but we have to say the International Data Space Association, but also the NIST, the US NIST organization for the National Institute of Standard and Technology, they all have developed this federation digital sovereign approach of data sharing. So it's not just a Gaia X play, it is actually a trend. How can I share data securely and keep the ownership, open up for SMEs, for others, that I'm a provider, but also a consumer of those data, because most of the companies have not sufficient data to run those great technologies. So for Europe, it's actually essential to build that data economy, the industrial data economy. When we hear platform economy, we are often, as a general discourse, are kind of afraid that the data are lost. So we see a trend from not just the data silos. There's probably pretty much a challenge also within the infrastructure industry, but leapfrogging into what is called mobilization or learning platforms. And we believe that the sharing could become a co-creation process, a multi-stakeholder process, where you have win-win situations for when public and private sector collaborate in a secure way, where also privacy is cybersecurity and privacy are realized. So we have, inspired by this federation platform, we developed an initial idea and structure of how this could look like. And you see, in order to share data with other or digital assets, not just pure data, raw data, but digital assets, you need a kind of what you see in the middle, a federator. And a federator, you say, oh, this the federator organization becomes the new monopoly about that. But there are different ways of federating.
Our next slot will be presented by Chao Li from the Chair of Architectural Informatics and Martin Slepicka from the chair of Professor BORRMANN, Computational Modeling and Simulation. And the title is Bridging the Gap Between Digital Design and Digital Manufacturing for Additive Manufacturing in the Construction Industry Association. So I think, Chao, you will start.
Thank you, Casimir, for the short introduction. So I'm very honored today to be here to talk about our research rationale and our methodologies about how to bridge such a gap. Okay, so. The concept of additive manufacturing and construction was not new since 2 decades ago. The contour crafting uses a large gantry systems to put the concrete material vertically layer by layer and aims to build up the whole construction online. And the D-shape approach uses the particle bed method, which can bring the higher level of geometry freedom. Some of the other companies has also deployed the advanced robotic arms during the printing processes to allow flexible printing path. And more interestingly is that this summer, the German's first 3D printed house was finished. Okay, in addition to these commercial cases, there are also something happening in the academic field. The TRR277, Additive Manufacturing and Construction, the challenge of large scale. This project is a transregional one and established mainly 3 focus areas. So the focus area A is about the material and processes. Focus area B is about computer-aided modeling and process control. And the focus area C about design and construction. It integrates the AM into a digital process from the BIM-based design to the fabrication. But normally the architects are not the experts of ANC. So they may be wondering if AM is really feasible for the design, or even further, which method should they choose for their individualized design? From this point, we'll conceive a design decision support system to assist the architects to make such a decision. But the first obstacle about such a procedure is that the AMC knowledge is quite diverse. A simple wall panel can be produced using different methods, like the particle bed one, or the extrusion method with lightweight concrete, or even the shotcrete one. These different methods differ from each other about the processes, the machine system, the material, and its effects on the final performance of the building component, and also about the degree of geometry freedom, the integration of the functionalities, and the assembly. We can describe, in fact, our knowledge into different forms, from the informal ones like the images and text to the formal ones like the rules and logic. The way that we choose to interpret our knowledge to a computer is what's called knowledge representation. This is a top-down approach of artificial intelligence. So we build up an AMC ontology using the description logic, and we use the rules as the counterpart to the knowledge, as there are some knowledge that cannot be formalized directly into the ontologies. So these 2 parts formalized the AMC knowledge base, and correspondingly, we integrate the reasoner and the rule engine to deduce the new assertions based in the input from the BIM model, like the semantics and the geometry information. Analysis was done upon that. Then it gives the feedback to the architects in visual or textual forms. The architects can correspondingly adjust their design based on this feedback. And the system then evaluates different criteria selected by the architects. After the decision making from the architects, the proposed methods will be given along with information. So this will help to enrich the BIM model in turn. We need to mention that the proposed design decision support system at this stage is not able to solely solve the decision-making problem by its own. In many cases, it has to integrate the simulation procedures. From this end, uniform data model, which holds a seamless information flow from design to fabrication, is quite essential. In this regard, I'll leave the stage to my colleague Martin, and he will elaborate more about it.
Thank you, John. I will inform you a little bit more about the data model we're working on. We base the data model on BIM modeling. Why BIM? BIM is already an established methodology in construction with which you can do a lot of tasks like design, engineering, logistical tasks, but you still cannot do fabrication directly with it. So what do we need for fabrication? We need to plan machine control. We need to maybe do some simulations on how the process is going on. And we also want to have some data feedback that we can compare as planned and as built models. So that's why we are implementing an intermediate layer, which we call fabrication information modeling. But what kind of information do we have to model? Is the information in the BIM model already sufficient? So is the geometry refined enough? What information of the semantics is necessary for our fabrication model? Have we more possibilities with the material? Can we have graded material, or does it have to be constant? And is some information missing, which we have to add later on? So, of course, with digital fabrication techniques, we can have more complex geometry, and we can also include voids in our structure, which is not yet implemented in BIM modeling. So for this, we can, for these kinds of models, we can use the BIM information, the boundary representation, and use slicing software to create printing paths, which then will describe inner voids and the hollowed out structure, which also helps us to integrate functionality to an object. Like if we include voids in this kind of wall, we can have an increased thermal insulation. So what we actually need is a print path to control the machine. And we need process parameters, machine parameters, and material parameters, which we have to linearly reference to the printing path. But is that already enough? So if we just have a line geometry, can we do 3D simulations with that? Not yet. So we need 3D information also of the printed object, not only the boundary representation of the complete object. So we also need a volume model that represents the printed object, including including the voids and the structure of the print itself, like the rough outer surface or something like that. And we also have not yet any means to store any data that we collect during the process. So we could reference to, every information to the printing path, but that would not be quite efficient. And also, we would not be able to do more complex motion control. Right now, as you can see here, it's horizontally sliced. So we use planar motion for this specific example, but sometimes it makes sense to do it a little bit differently. So if we have a building like this or a structure like this, it might not be a good idea to slice it horizontally. As you can see in the top layers, there's a large overhang and it could not be printed in that way. So we might have to do something like this. But the motion control of something like this is a bit more difficult. So the printing nozzle cannot print directly from the top. It has to align with the surface of the slice. So what we also need to control this motion is an orientation vector of the machine for the machine, and that information can be directly used from the surface we already have, because we do the slicing beforehand. So if we retain that surface and reference the printing path we create from it on that surface, we have both informations. We have the normal vector of the surface and we have the positioning of the curve with the curve. Yeah, to put it more into something you can grasp better, I made this animation. So the printing path here stores positions for the motion control and also acts as a referencing system for fabrication information. So all the parameters we created. And the layer surface acts as a reference system for the orientation vector. So if we position our nozzle along the printing path, we can use the normal vector of the plane at that position to control the orientation of the robot. And also, we now have the opportunity to store sensor data on that referencing plane in the UV space of this surface. So if we attach a laser scanner, we can measure distances and we can check if it deviates from the layer surface and store it as a heat map on that surface. Additionally, if we add a bounding surface model, we can also have this as a referencing system for later measurements if the print is finished, and we can use it for post-pressing of the surface and further steps later on. All right, that's it from my side. Thank you for your attention, and we are open for questions.
Are there any questions from the audience? If not, I would say, as we already proceeded a little bit longer, you can also ask directly in the coffee break. We prepared some cake and coffee in the back, and we will be back in 20 minutes at 3 p.m.
Yeah, hello, thanks for the invitation today. 3 years ago, we went on a journey together with the chair of computational modeling and simulation. It was a journey on data consistency. This journey ended now in September, and first of all, I would like to thank everybody who was involved from that chair for his great contribution and passion that made this project such a great success. Why are we interested in data continuity? Our vision is that if you look at this bridge here, to realize this bridge over the whole value creation chain, there's hundreds, sometimes thousands of people involved. And we know that if we can deliver better communication in these projects, we will improve the value creation over the entire life cycle of this bridge. And we will come to a better collaboration, to better projects, and to better and higher performing buildings. So, why is data consistency so important? So you can see here, this is an image of the Nemetschek group. So we are a fast-growing company, and we have today 15 brands. That is here, you can see here, in 3 different divisions: design, construction, and manage. And if you look in there's dozens of tools in place we deliver, but if you look in our projects, it's even stronger. There's maybe hundreds of different tools people use, and each of these tools create an own data silo. And these data silos, they are accepted by the AC industry because the industry is fragmented, and they work and they think in silos. But if I look,
in a crystal sphere of the future. So how will the world be in 10 years? I know that these silos, they will break up. There will be much more collaboration and integration. And that's why data consistency is one of our strongest goals, but it's as well a big challenge. So if you can have a quick look here, we have in the BIM projects, BIM data, there's a graphical and there's non-graphical BIM data, and we have more and more digital documents. And we can handle already quite well. There's hundreds of different models that are there. There's different revisions. There's native models and there's open models from different stakeholders over time, but we can handle them quite well. Our approach is that we take these files, we extract the objects in these files, and we map them into a database in the cloud and come up with a solution for a more linkable and more consistent data management over time. Our, let's say, black point here are the documents. Documents are, let's say, unstructured. There is lots of images, there's contracts, there's plans, there's photos, and all of these documents disconnected from the models. And our goal would be to connect them better and use the same approach, make this document smart, understand what is in this document, and automatically link them to the models. Of course, the idea behind this is to use here artificial intelligence. Machine learning has come to structure unstructured data, and there is an, let's say, a well elaborated approach over the entire life cycle to use artificial intelligence in our groups. You can see here as well siloed many different use cases in design, construction, and in operation, but there's as well a layer of fundamental AI services. And these fundamental AI services are, for example, point cloud classification, there's voice recognition, and there's something we call deep linkage. That means an automated linkage of different data sources in the project. So this is our scope. This is what we tried to achieve with the project, and Jimmy will tell you how we did it.
So for the deep linkage topic, here we focus now on the linkage between 3D models and digital drawings in this specific part of the project. So you heard already multiple times through the day that BIM is very beneficial. There is a lot of advantages for it, of course. It's good for coordination, doing a lot of simulations, maybe from the early phases, and quantity takeoffs and so on. And that's great, but still it's not the only source of truth in the practice today. So the industry heavily relies on other sources, and the main one of those sources is the digital drawings for the different purposes. So there are different actors doing different kind of the development for the project using different tools, and many of them still prefer and use also digital drawings, aside their obligatory requirements for permitting and submissions, and as well for they have well-established legal aspects when doing delivery and submission for the different projects. In addition to this, there are a lot of very highly detailed components that are currently only provided using drawings, and drawings are still one of the most preferred medium of information on construction sites. So this means I'm not trying to convince you to use drawings. I'm just saying drawings are very well established in the industry and in today's practice, and we have to keep in mind this coexistency between drawings and models. And since we have those and people will keep using drawings, we need to ensure the consistency between those two words and make sure that we have a connected source of information. Okay, so when we started this project, we started thinking about the typical workflow from practice. So if you use a BIM modeling tool, from there you can deliver a 3D model that can be maybe a native format or an open format. And also at the delivery, everyone delivers a set of drawings. Later on, those drawings are used maybe in construction site or by different disciplines for different purposes, and they are edited further in a drawings editor software. Then from there, you will have additional changes. This will cause that we have here a set of drawings that are different from the delivered drawings at the very beginning of the project, or at the end of the project, sorry. And then, which cause that we have inconsistency between the final state of those drawings and the original 3D model. And this will cause a lot of problems. For example, this 3D model will lose the trust of the people who use it, and it will be an outdated source of information that just stand there and not useful anymore. And we don't want this to happen. A simple example that comes from practice can be just shifting some of the elements. A small shift in any of the elements from the drawings will let everyone lose the trust of the 3D model, which isn't really good. So we have this problem, and for this we propose an approach that starts with, first of all, we want to identify what kind of changes happen to those 2D drawings after modifying them. And to make sure that we have a consistent 3D model, we want to provide a deep linkage between those drawings and the 3D model, and then incorporate or provide specific warnings about those identified changes that happened later on in the project. So for this, we started, let's assume we have a 2D drawing on one hand and have a 3D model. First of all, we want to know where this 2D drawing belongs. So is it in the specific, in the first story, second story, is it at the roof? Where is that located? And after that, we want to check how can we align this drawing with the 3D model to give more meaning to the 2D drawing. So the 2D drawing is not smart at all, just lines and symbols. So we need to give it some intelligence and bring some more information from the 3D model to those 2D drawings. Okay, so after we match those, then we can identify the changes and bring those changes to the 3D model, or at least provide a warning where those changes have happened or changed. So for this, the first approach we did, which Professor BORRMANN already talked about in the opening, it's about localizing or finding out which story is representing this specific drawing. And the approach is based on a well-known methodology called geometric hashing that makes some sort of geometric description of descriptor of the geometry of the story and compare it with the entire building. So for this, we developed a tool that makes multiple cross-sections of the 3D model. And you can see here the cross-sections generated on the upper right or left for me. And then the geometric hashing is performed on the both 2D representations. So here, as you see, we have this story selected in green, which means the similarity of this geometric hashing was the highest for this story, which means we know now that this drawing belongs to this story. So after identifying the story, now you can see here I just showed a small piece of the model. We have only one story now. So we zoomed from a building to a story, and we want to match the elements or highlight the elements from the 2D to the story or the 3D. And for this, we came up with the idea to use the windows and doors as a fingerprint of the elements inside the story. So we want to use those to, let's say, dock this 2D floor plan over the 3D model to align those elements together. Yes, and so here there are two sides that we need to process the drawing, and we need to process the 3D. For the drawing first, we need to identify elements. We need to find out where is door, where is window. And for this, we started with training a neural network that can identify windows, doors, and walls. And so for this, we collected a lot of data from online sources and data sets that are shared online. and did a lot of labeling and found a lot of labeling online for those that we combined together and trained multiple neural networks on them. So here we used the state-of-the-art neural networks, and also we developed our own neural network, and both of them gave very satisfactory results for detecting the elements. So the assumption is, if we get an original floor plan like this one, then we can give it to those neural networks and get then out of this a segmented floor plan that can tell us the different kind of objects that we found out. Then from this segmented floor plan, usually you know that it's like per pixel segmentation. So we have a lot of deviations here and there and some missing pixels and things like this. So this is why we perform post-processing on them to have just take only some bounding boxes of those elements, and then at the end we calculate the center points of them. Then if we go to the other side, to the 3D model, we thought first of querying the 3D model, because for example in BIM Plus you have an API, you can query models, get their information, get the geometry, do all of this, but it's a lot of work to really generate them in a comparative positioning like the 2D drawing. So this is why we also take a cut of the 3D model and generate out of it a floor plan. That's smarter, not just an image. It's a smart floor plan that's using a rich SVG format. It's like an XML format that you can add for every line and every pixel inside this SVG more information like the IFC class and the GeoID and so on. And then using the same way we calculate the bounding boxes and the center points. So this brings us to two sides. We have here the original floor plan and the floor plan from the 3D model that's smart. And now we want to match those. So we simplified the problem of matching 2D to 3D to really just 2Ds and center points. And here we try to assign every center point from this side to another point from the other side and measure the distances. And we do this while rotating one of the images for 360 degrees. So we calculate this over like a cycle. And then the one that gives us the minimal distance between the points is the one with the highest probability that those images should be aligned with this kind of orientation and way. Even this helps with changing the dimensions and with resizing the images to fit each other. Then once we have this, we transfer information from the 3D side to the 2D side by transferring the GeoIDs, and those GeoIDs can be enough for even querying more information and doing more things. Yes, and then after this, after we find all those transfer GeoIDs for windows and doors, we also do more reasoning on the other remaining pixels. It can be columns, it can be walls, and so on. For all of those, whenever we find an overlap, we also transfer information from the rich SVG to this new floor plan that has, that it will take, we will transfer the classes and the GeoIDs from that. So, and the result from this will be what we call smart drawings that will really make drawings smarter. Instead of just lines, we have lines that have meaning. And this will really bring the connection or the linkage to the 3D models. So here you can see this highlight is the IFC GeoID. And what you can do with this is, in this XML, it can be opened also in web viewer if you want. So we can add on-click event. Whenever you click on one of those XML lines, then get the ID of that, just basic JavaScript, and then query this 3D model and highlight it with what was selected. So this can be a very simple way, and then you can query more information from the 3D model using this technique. Cool. So now we aligned, we localized, we aligned, and we want now to detect more things about the changed elements. So here I just show very simple examples. In our test cases, we really went into much more complex use cases. So here we can have an added element, or some elements were switched or moved. And for this, we apply a technique to find the differences between the original and the changed floor plans. And this will give us this kind of differences image that looks like this. Then we take those and run them again in the same neural network. But if I just identify the symbols, so we can know that this is a window, this is a door, this is a wall that was added or moved. So this shows the differences from both images. So we have what it was and what it became later on. And we apply reasoning, and this reasoning is applied in combination to the floor plan. So whenever we already have a door, for example, on the same wall, and we find out that in the new one, there is no new wall, but only one wall, but with different position, then we assume that this door was moved. Like as you see here in this case, this door was moved, but not added to the room. The same with other things. So we check what we have before, what we have now, and we reason about what kind of information within the wall or within the room. And then we bring this reasoning to the 3D by, say, notifying that we have here something inconsistent. You can change it, you can update the 3D model. Cool, so we have this. Now, if we want to bring this more into practice, how can we bundle this together, the 2D and the 3D in one source? I mean, all of us talk about digital twins, everything, a lot of sources connected. And this is where we said, okay, we want to have an information container that puts everything together and connect it together. And then this information container, for example, can be handed over to BIM+. All what BIM+ have to do, have just to read those links, read this connection, and can provide two information with linkage, so with interactivity as well. So here we work together on different approaches. Since SVG is XML, there is also IFC XML, for example, and we investigated this kind of one-way connection. So here we have one direction connection from the SVG to the IFC file. And we also investigated another approach that's based on linked data, where you have some index and some RDF links that specify the connections between files and between the elements inside those files. If you want to read more about it, just search for information containers and for those ISO standards. I'm coming to an end. Cool. So that's all from my side. I would like to finally thank again our sponsors, and especially Stefan also for his support during this project. It was like multiple years of support. Yes, and thank you for everyone for your attention.
Then we will, thanks again for your talk. We will come to the next topic, which is from our other LOC premium member, Virtual City Systems. Welcome Stefan Trometer, who's giving the joint lecture of you and Bruno Wildenborg about coupling urban microclimate simulation with semantic 3D city models.
Thank you, Casimir. Ladies and gentlemen, welcome. Within the next few minutes, I would like to give you a short update what we did recently in the field of urban microclimate simulation. But that's not only my work, it's also the work of the chair of Geoinformatics and Bruno Wildenborg, who was included, and especially Tobias Kraut, who did his master thesis within this topic. My name is Stefan Trometer. I'm from Virtual City Systems. There I'm responsible for urban simulation and business development. We are part of CADFIM Group, and through this we are linked to the Leonhard Obermeyer Center. We are experts for 3D city models, and especially focusing on information models like CityGML in this context. What you see here is what you can do with our software solutions. You can set up a 3D city model platform like the one for graphing we see here in this screenshot. With this city model platforms, our customers set up information platforms, they do city marketing, and step by step they are doing urban planning. And now we're coming to the more interesting topics linking the city model platforms with urban analytics and even with urban simulation. And the topic of today is a very interesting, very special topic at least, which is really in the field of urban simulation, and that's my background as well, and so I'm quite happy to give you an update on this. What you see here is Rotterdam, which is one of our lighthouse customers, and you see what these city model platforms can include. You see the buildings, you see the tree cataster, but you also see all the infrastructure lanes, and you bring it together in one city model platform so that it can be used for all kind of further applications. But what you see here for Rotterdam is not only for the big players, this is possible also for the small cities, like Grafing near to Munich, not far away, and a lot of others. We used this kind of city platforms, and we always try to find new applications for these models. And of course, we all know the topic, urban heat islands. So we are faced with climate change. We are faced with more heating up in the summer period, especially in the city centers. And we thought about what we could contribute or how we could help to help in this situation. And if you look at that screenshot, it is more or less obvious that the temperatures in the upper picture are a lot higher than in the lower one. But the question is how to come from the scenario of the above picture to the one below. And if you think about measures, it is not so easy, because the question is how concrete measures really affect the situation. And it's not about doing something. I think it's about trees help. I think no one would say anything else. But the question is how many trees you need, or where they should be, or how big they are. So if you want to plant a new small tree and you wait 20 years till it's big, till you have the effect, you calculate it. And of course, there are questions how green roofs or facades contribute to these positive effects, or whether there is still a positive effect for an urban area from one green facade. So these are things which have to be evaluated for every single case. And where we are working on together with Thomas Kolbe and his team is a solution to support this not so easy process. The idea is to use the city model platform and to link it with an existing solar potential analysis tool, and then in addition to link it with Answers Discovery, a simulation tool, an intuitive simulation tool which allows you to perform wind and thermal simulation. So the concept we followed here, and we follow for almost every other application as well, using the interactive map, then going into the special topic, the special solver, like the solar and the heat simulation for this example, and then bringing the results back to the interactive map. So we have the 3D city and terrain model as basis, but then we can update it with buildings if there have been any changes. We can include planning models, we can include vegetation objects, which are necessary for this kind of application, and of course we can add land use. Is the surface sealed, or is it green? And of course, on this basis, we can select an area which we want to investigate. Then we go to the analysis block. We use the 3D solar potential analysis, which is a tool which was developed by Professor Kolbe and his team, which allows also for calculating vertical surfaces, which allows for calculating shadowing effects from all kinds of objects. So in the end, we use this for defining boundary conditions, simply said, to distinguish between where is light and where is shadow. with this boundary conditions, we go to the wind and thermal simulation. There we use ANSYS Discovery, as I already mentioned, which is user-friendly and more or less real-time. So it does not take days for calculating a result. So we have a more or less interactive and easier approach. And in the end, we really want to go back to the interactive map, where we can visualize the results. But we will see it afterwards in the application example. These results have to be prepared in a way that they are becoming understandable. If we want to achieve this, we can compare different variants of plannings, of ideas, and we can do this more or less interactive, and this, of course, supports objectification of discussions. And so, in general, we believe that this really helps in participation activities. The tools we use, the solar tool, we see here an example. It is used, yeah, it works. So we set up on existing solutions, like here for Helsinki. We also use the ANSYS Discovery already. It's also an example from Helsinki, where they built a smart city quarter and they compared the simulation with the wind tunnel effect. So also this solution is more or less validated and we set up on this level. So within the scope of the master thesis of Tobias Kraut was the adoption of the solar tool, because we could not use it in the way it was. The second part was the selection and export of the scenes in the 3D map, the generation of boundary conditions for the simulation, then of course performing the simulation and evaluation of results, the preparation and visualization of these results, and last but not least, all these single steps should become part of an automated cloud-based, cloud-ready process. And of course, you know and we know that there are other solutions on the market, and we really want to focus on not on the mesoscale models. We want to focus on microscale models going in the area of building models. So this is really the focus area of this solution, where we think that we could have a positive contribution. So this is the test case which was investigated by Tobias Kraut within his thesis. That's just in the city of Bremen, where we right now have an ongoing project on urban heat island simulation. And what you see here is the city GML model, and here you see nothing, it's without trees, and here we have the same scenery with trees. And the question was, what is the calculated difference in heating up due to these trees? What you see here is the model which was transferred from the city model to ANSYS Discovery with the boundary conditions from the solar tool. And then you get results like this. So these are the physical results, and then you really have to think about whether it's good or whether it's bad and what happens. You try to understand the result. So if you look here in the area, you see here the trees, and more or less it's, let's say it's not yellow and not red. And here in the center, the same area in the square without trees, it's yellow. So it gives you the impression that it's hotter on the right side. So, but now you want to bring this information into the city model, and you want to define a result in a way so that you can make a decision upon it. And one approach which seems to be reasonable is to evaluate the temperature change for the difference between with trees and without trees. And what we see here on top is just the temperature difference between those two planning variants. And here it is visualized within the city model. And now you can interactively experience your city model, and you see if you have these kind of trees in this position, in this size, then you will have a probable lower temperature in these certain areas up to 6 to 8 degrees. So for what I just showed, we see the potentials really in the evaluation of planning scenarios with respect to specific impact on local temperature effects for special heat scenarios. So this approach is rather fast, and so it's really applicable for early planning phases. It's individual because you can interactively adapt or evaluate, evolutionary further develop your scenario. You can change it very easy. And then it becomes comparable. You can compare 2 or 3 or 4 different approaches. And in the end, we always try to define solutions which are user-friendly. So this means that you do not need experts for the application of these scenarios. I'm ready. I'm finished. Thank you for your attention. And just let me make one last point here. We have this certificate course where we had the first very positive run this spring. The next round is in March. It is in German, but there will be an English version, a virtual English version also next year. This is planned. We are we are setting up this course. So thank you very much and have a nice afternoon.
Thank you. Thank you, Stefan, for your inspirational talk. Are there any questions from the audience? Because if not, I would have one. How did you model the trees? So are there also, or are you thinking about dynamically modeling the trees because they have seasonal effects, but also growth rates included? So this is a major impact on that.
Yeah, of course. If you look at these scenes, they are rather complex, of course, from geometrical effects, from the physics which happen there. But yeah, I'm a civil engineer. You have to simplify those things. So the advantage is that we are rather fast and it's user-friendly, but of course we have to simplify on the other side. And in the end, we always try to do it in a as good as possible way. And then of course you can also compare which is the difference between having trees or having no trees. And this is the basic idea we follow, and I think it's important to add here that we believe that that's a good tool, or that it might become a good tool for early stages of planning. But there are, of course, still expert tools which have to be set in to do it in a real professional way. But the problem is that these tools take time, they need other experts, and in early stages of design where you decide how it should look like, these tools are lacking right now, and there we think that we can contribute.
Okay. Then thank you very much.
Sorry, I have got a question. So
yes, sorry.
Stefan, thank you for the presentation. A spontaneous idea came when you showed the picture of the street with the cars in it and the trees and without trees. Is there a fact of movement of traffic to this question of temperature? If yes, have you ever coupled a traffic simulation with the model?
So in the end, as far as I know, there are, of course, local effects due to passing cars, but these turbulence effects are, yeah, let's say they are in a limited area. But in the end, that's real, but in the end, that's very difficult to calculate or to take into consideration. And this is one of the points where you have to distinguish between, is this enough, or shall I go more into detail? But as far as I know, it's of course possible to calculate these turbulence effects, but for single cars, I'm not sure whether for many cars, and in the end, I also believe that there are simplified approaches how to determine the affected area by these car turbulence effects.
Danke nochmal, Stefan, sorry, für die Q&A-Runde, und als nächsten Slot möchte ich unseren neuen Premium-Member von der Innovationsmanagement Bau vorstellen. Die werden zusammen das Forschungsprojekt, was jetzt anläuft, vorstellen, Data Mining in der Bauausführung, As-performedconstruction Processes. Aber zunächst möchte ich Herrn Michael Thon, den Geschäftsführer von der Innovationsmanagement Bau, begrüßen, der einführende Worte vorträgt.
Hallo, ich möchte zusammen mit dem Alexander Braun Ihnen unser Forschungsprojekt vorstellen und im ersten Schritt einfach mal die InnoBau vorstellen, weil wir ja der Neuling sind hier. Ja? Bisher kennt uns noch niemand. Andere Richtung. Ja. Also unser Motto ist gemeinsam mehr erreichen. Stellt man sich natürlich die Frage, warum tun sich Baufirmen zusammen, die sonst im Wettbewerb stehen, um Innovation zu betreiben? Die machen das aus einem ganz einfachen Grund. Wir haben Geld. Ja, wir sind Mittelständler. Wenn wir 2% unseres Umsatzes für Forschung und Entwicklung in die Hand nehmen, ist es eine Viertelstelle. Ja, mit einer Viertelstelle kommt der Herr Professor nicht weit. Ja, wir auch nicht. Also der Viertel der Arbeiter bringt auch nicht viel. Deswegen tun wir uns zusammen und haben im Endeffekt uns eine, wie man das heutzutage macht, eine Vision gegeben, indem wir einfach sagen, wir wollen Raum für Neues schaffen. Wir wollen zusammen im Endeffekt nicht jeder in seiner kleinen Experimentierküche etwas tun, sondern wir wollen zusammen etwas tun und wir wollen das auch zusammen mit Ihnen tun. Also mit anderen Firmen, mit den Universitäten, mit anderen Forschungseinrichtungen einfach schauen, dass wir nach vorne kommen. Das tun wir, indem wir für uns selber gesagt haben, Vernetzung steht ganz oben sozusagen auf unserer To-Do-Liste. Nur wenn man ins Gespräch kommt, nur wenn man Sachen diskutiert und auch Sachen kontrovers diskutiert. Ja, und immer dieses Nicken, das bringt uns nicht weiter. Kontrovers diskutiert, dann entsteht etwas Neues. Wenn ich dazu dann noch im Endeffekt tatsächlich aus diesem Forschungsansatz einen Entwicklungsansatz mache und sozusagen schaue, ist es anwendbar, was der Forscher sich da ausgedacht hat und in seinem, sage ich mal, durchaus Experimentierkasten sich erdacht hat, dann kommen wir langsam dahin, wo es für den Unternehmer interessant wird, weil der Unternehmer ist immer derjenige, der dann sagt, jawohl, da machen wir ein Produkt draus. Das ist marktfähig, da kann ich etwas draus machen, das interessiert jemanden, da kann ich einen Nutzen jemand anderes dafür versprechen, oder ich kann es für mich selber nutzen, weil dadurch meine Produktion besser wird. Ja, oder meine Prozesse werden dadurch besser. So, wer sind denn diese gemeinsamen Menschen? Ja, das sind diese Baufirmen, die Sie da sehen. Ja, zusammen machen wir 1 Milliarde Umsatz. Das ist in der Hitliste, wenn man die deutschen Baufirmen als Hitliste mal runter sieht, dann ungefähr Platz 14. Ja, also wir sind nicht ganz oben, wir sind kein großer Player, sondern eher im Mittelfeld. Es stehen aber 4000 Arbeitsplätze dahinter. Ja. Und uns ist das immer ganz wichtig, weil wir als Unternehmer leben im Endeffekt von der Handarbeit und der Kopfarbeit unserer Leute. Ja. Bei uns wird das Geld draußen verdient und nur wenn der Handwerker das versteht, was wir wollen, kann auch im Endeffekt am Schluss ein reales Produkt in Form eines Bauwerkes entstehen. wie schauen denn bei uns diese Prozesse aus? Also wie schon gesagt, wir setzen immer bei dem Forschungsansatz an. Ja, wir haben uns da im Endeffekt sozusagen überlegt, ja, das nennen wir ja Innovationsscout. Also da ist jemand unterwegs, der schaut, was tut sich so am Markt, wo entsteht irgendwas, worüber denken andere Firmen nach, gerade in der Softwarebranche oder im Bereich der Robotik, wo tut sich was? Daraus entwickeln wir dann für uns sozusagen ja, Ansatzpunkte und sagen, jawohl, da hat jemand von den 7 Mitgliedern Interesse, also er hat einen Ansatzpunkt und sagt, okay, da kann ich etwas beitragen. Das nennen wir dann Jumper, ja, also so dieses Gummiband, was wir da erzeugen wollen, um den mit herzuziehen, aber auch im Endeffekt wieder etwas zurückzugeben. Also wir sehen das nicht als Einbahnstraße, sondern tatsächlich so wie ein Gummiband. Immer anziehen, nicht zu stark, dass es reißt, sondern immer schön ziehen, ab und zu mal ein bisschen schmieren, dass es elastisch bleibt. Und am Schluss dann tatsächlich das innovieren, also auf den Markt bringen. Und da unterscheiden wir dann für uns immer selber, bringen wir es sozusagen, bringt es einer einzeln auf den Markt, weil es irgendetwas ist, was jetzt nur einer von diesen 7 anbietet, weil wir die ganze Palette des Bauens abdecken. Ja, also wir sind in der Rohstoffgewinnung, genauso wie in der Projektentwicklung, im Industriebau, im Wohnungsbau, Infrastrukturbau, genauso dann nachher wie in der Instandhaltung, Beseitigung. Also wir decken diesen ganzen Kreislauf des Bauen ab. Wir machen das auch alle eigentlich mit teilweise eigenen Planungskapazitäten. Also wir führen nicht nur aus, sondern wir planen auch selber. Ja? Und da kommt eben immer unterschiedliche Ansätze, wer kann mit irgendetwas anfangen. Und da kommen wir dann eben zu dem Bezug dann zum BORRMANN, zum Alexander, wo wir gesagt haben, okay, was interessiert uns denn jetzt mal ganz besonders? Wir sind ja Produzent, also wir produzieren etwas. Die Baustelle. Oder anders formuliert, es ist ja nicht nur die Baustelle, sondern es ist ja immer eine ortsgebundene, also die Baustelle, oder eine ortsungebundene Produktion, die wir machen, also wenn es dann in irgendeinem Fertigteilwerk zum Beispiel stattfindet. Und dann einfach zu sagen, okay, was passiert denn da eigentlich? Das, wo viele sagen, ja, das ist ein alter Hut, Refa macht das ja schon seit 1930 oder sogar noch früher, 27, glaube ich. Oder in der Automobil, die machen das ja auch, die machen so Erfassungen, wie die Leute sich bewegen. Das ist alles richtig, bloß der Bau macht es nicht. Ja? Wir haben einmal in den 90ern damit angefangen, mit unseren eigenen Leuten so eine Art Bauarbeitsschlüssel zu erfinden. Also da hat der Kappa auf der Baustelle pro Stunde noch aufgeschrieben, ja, da hat er jenes gemacht, da hat er dieses gemacht. Ja? Können Sie sich auch vorstellen, wie begeistert die Kappos waren, wie sie das gemacht haben. Ja? Besonders hat man das dann irgendwo in große Datenverarbeitungsmaschinen eingegeben und das Produkt, was rausgekommen ist, war eigentlich mäßig. Ja? So, also haben wir uns gedacht, müssen wir mal Daten erfassen mit der ganzen Problematik, die dahinter steckt, weil wir ja Indoor arbeiten, genauso wie Outdoor. Wir im Endeffekt mit sehr viel Stahl teilweise arbeiten, also im Endeffekt immer mit irgendwelchen Barrieren zu tun haben, die Sendeleistung einschränken. Und wir im Endeffekt ja auch viel Wert legen auf den Bereich der Arbeitssicherheit. Also das sind so kleine Geschichten, wo wir dann immer merken, oh, da stoßen wir an bestimmte Grenzen, weil das sicherheitstechnisch dann nicht mehr geht. Ja? So schöne Beispiele sind da, wenn ich immer höre, ja, da gibt es so einen Roboter, der fährt bei Ihnen auf der Baustelle rum. Ja, auf vielen Baustellen gibt es keinen Platz, wo ein Roboter fahren kann, weil ich habe die Straße, wo der Roboter fährt. Dann muss ich ja noch einen Sicherheitsabstand halten. Und wo ist dann der Mann? So, und da haben wir dann eben gesagt, da brauchen wir jemanden, der uns hilft im Bereich der Datengewinnung. So, und da setzt eben dann der Aspekt an, wie ich gerade gesagt habe. Das ist nochmal das, was wir uns an Zielen gesetzt haben. Und das war der Startpunkt eigentlich, den Alexander mit seinem Team zu sagen, okay, wie lösen wir jetzt das Problem? Mit welcher Forschungsleistung können wir da hingehen und können sagen, ja, wie schaut die Nuss überhaupt aus? Ja, und wie knacken wir sie dann eigentlich dann am Schluss? Ja? Und jetzt ist das dein Part.
Genau. Perfekt. So I switch back to English for the international audience. We actually took this opportunity over to start working on our joint project on data mining in the construction processes. And to start off, I want to show you this picture, which is, I think, very well designed to explain the general task or the problem we are facing. If I look at this picture, or actually if all of us, which we are all from the construction industry, look at this picture, we see a construction site which is under progress. So we see there is a concrete truck coming, we see several stages of construction currently happening, and I, as being involved in this construction site, also know that we have several different stages of construction on this construction site. So for example, right here, the first floor walls are already finalized, concreted, while as directly next to it, they are still under construction. And with this information, and also knowing that there is a lean process in place, I can directly infer a lot of more information from this sole image than any computer at the moment would be capable of doing. I mean, for the computer, this is a lot of pixels. And our task is to gather all this information, to join all this information together from all these different data sources we are currently already having, and gain additional knowledge from that. So we started this project, and Fabian Fitzner from my group is working on this project. He's today still on vacation, so he just finished his master thesis and is very happy to have finished it and will start soon on this project again. And we are currently working on this first case study, which is the building lab in Regensburg, which was already briefly introduced. And it is constructed by the company Donaubaeuer, and we are very happy about this collaboration. And to start this off, I want to show this, I think, very impressive image, which is really showing a lot of cool things. I mean, to start off, there's a guy climbing on a crane, which is always kind of nice. I would like to do that too. But I think another thing which is very important on this image is that the trust we got and the opportunity from the construction industry, in this case from company Donaubaeuer, to work on this site, to place cameras on a crane, to get all this information, gather all this data, is really, really important for us, because only if we get this data, we can really work on our problems. And in recent projects, we often had this problem that we were not able to, we had a lot of cool ideas. We're thinking we could throw a lot of algorithms on problems, but we did not have the data for that. And here we have the possibility to do that. We placed a lot of cameras on the crane, equipped the whole site with Wi-Fi, did a lot of fancy stuff to really be able to gather the data on this construction site. And you already can see some of the first results here. So these are the webcams that are working on the site, continuously streaming all the data, all the images, where we can already see the activities that are going on the construction site, which is already a very important first step for us to get to know the current status of the site, to know about the processes that are currently going on there. With this, we do not only get the images, but because of the fact that the crane always covers the whole construction site, we can actually get a view from different angles of all the elements on the construction site. And with the help of that, we can do a 3D reconstruction with photogrammetric methods to get actual 3D information from these 2D images we initially had. And this enables us to gather additional information from these processes. In addition, we also placed we did continuous laser scans on the construction site that also allowed us to gather high quality detailed data from all the current statuses on the construction site. This work has been done together with Professor Stockbauer from the OTH in Regensburg, we are very, very thankful for this collaboration that they also supported us here on this construction site. This is one of the results that we are getting, and you can already see we're talking about 72 million points from only one current status. So tons of data, we don't really know what to do with that. To start off, we started with a scan versus BIM process. So we also have this BIM model. We can compare the geometric point cloud with this model to get first information on this. And this already combines several data sources, which is one of the key aspects that we are facing here. So we want to combine the different data sources like geometric information, process information, semantic material information, and so on. And only if we bring all of this together, we can actually gain additional knowledge. To further enhance that, we started tracing the activities on site. So we really tried to get a sort of a heat map where the actual work is happening. And what you can see here is a first research draft we focused on to really get some deep information. Where are the workers currently working? What is the current status? So combine again worker position with actual work that is happening and check how does it correlate. Are the workers actually working on these projects, the actual problems that we are facing on the construction site? An additional data source we are using are thermal cameras on site. So we will be placing a thermal camera on the construction site to get another layer of data sources that we can then integrate in our whole system. So finally, we really want to have this huge database where all of this information is combined that is then allowing us to gain further knowledge on all of these processes. And to sum that up, what I just showed you was basically the very first step of data mining. So we are currently gathering tons of data, and by tons I mean we already have around 40 gigabytes of image data. We have several, trillions of points from point clouds and so on. So really a lot of data from different sources. We combine that with all the process information, material information, and so on. And all this information combined then allows us to find patterns in this data to get this additional knowledge we are interested in. Like, for example, we have problems on the construction site because the workers are in an idling mode. They are waiting for the concrete truck to arrive because it's stuck in traffic. That's quite a common problem. And to identify these problems, we need this. I mean, some of these problems obviously could also be done manually, but to identify these huge interactions between all these data sources, it is important to have these possibilities of data mining to find these patterns in the actual data. And then finally, we will be able to evaluate this and optimize the construction processes, and maybe also cost and planning. And that's it for the moment. Thank you very much.
Are there any questions from the audience? Yes.
Well, thank you very much for the very interesting presentation. Do you have made already any decision about maybe what document management system or what environment you would use to manage all that really huge amount of data? So are you thinking about using a Kubernetes cluster or something like that in the cloud, or with using some specific document databases, etc.?
Well, to start off, the current data we are storing will be stored in a non-structured MongoDB, which is, however, not the final form we are planning to work on. So we are already storing a lot of data on the AWS cloud. However, we are also facing some privacy issues there with storing data on international platforms, and so that's why currently we are still trying to store the data on-premise at TUM, which is why we are currently more or less trying to store the data in-house as good as possible. But we are well aware that this will not be sufficient for the whole, if we're talking about all the data I was just mentioning. So this is definitely something we need to address.
Okay, then thank you, Alex. Thank you, Michael, for your presentation. And we're coming to our next slot from our premium member, Obermeyer Holding. It's a joint project, RailTwin, the quest of multi-source parametric railway capturing. Maximilian Bade will start, and then Felix Eichler from the Chair of Computational Modeling and Simulation will take over.
Thank you very much. Right, so my name is Maximilian Bade from Obermeyer Infrastruktur. And I'm happy that I can present you our joint project, RailTwin, the quest of multi-source parametric railway capturing, which we are doing together with the TUM and Provi GmbH. Right, the team of a project, I already told you that, it's the Leonhard Obermeyer Center, the TUM. We as Obermeyer Infrastruktur GmbH und Co. KG and the Provi GmbH. And very important, the project is supported by the state of Bavaria and co-financed by them. We are right in the middle of the project period, so we are happy that Felix from the TUM can show you later some results, some first results. But in the beginning, I want to show you, we call it the birth of the idea, how we got there where we are now. We at Obermeyer had lots of refurbishment projects in the network of Deutsche Bahn. Normally, these projects have a length of from a few hundred meters to like 10 kilometers. You have to work over the rails, over the tracks by feet. And in 2016, I think we got this project. You can see here the refurbishment of the high-speed line between Mannheim and Stuttgart. The total length of about 100 kilometers of the route. So the first task was that we should have walked by about 200 kilometers of tracks. So this was not possible for us, and it also isn't really sensible. So we started to develop a digital data twin together with Provi, which made it for us possible to pick obstacles right in point clouds and put these obstacles, which normally you have to detect on the side, directly into a database with consistent attribution, and we were able to get the required documents and forms out of this database. But it was kind of a really semi-automatic process, or there's a lot of handwork to do. And 2 years later, we got this project with even more tracks to refurbish, the high-speed line between Kassel and Würzburg. It's about 100 kilometer of length of this route, so nearly 400 kilometers, which would have been researched, which would have been done manually again. And it was like that was a point where we thought the first time that there has to be more, and we started to talk with TUM, and we together we established our project RailTwin. because after all these projects, Mannheim, Stuttgart, Kassel, Würzburg, and a few more, we see there's so many different important classes of obstacles on railway infrastructure, like, and I have to tell it in German, like Heißläufer-Ortungsanlage or Schienenauszugsvorrichtungen. And all these obstacles you can see with our engineers can see them, but there are so many different that our manual process came to its limits. At the same time, we had an evolution of data capturing, which gives us the possibility to get the data we need for RailTwin. This is very important, and Felix asked me to tell you this. The data we use for RailTwin, and he uses and shows you later for his study, we use this mobile mapping system with 3 laser scanners and 2 cameras. And more importantly, because we are in the railway network from Germany, we have to get the track geometry very more accurately than you can get it out of point clouds, out of the mobile mapping system. So there's another system using sensor fusion on the measuring system we use, but yeah, it's more like a side fact. And now, where I want to give the floor to Felix, the project Offenburger Tunnel. It's a bit smaller than the big refurbishment projects we did, but here we have this data for the first time we can use for RailTwin with the 3 mobile laser scanner system. And all right, sorry, I forgot that. Before I give the floor to you, we sat together like a few months ago in our RailTwin consortium and thought, okay, we have the high-speed lines, we have smaller tracks, like we did a measurement in Schwarzwald, it's the Schwarzwaldbahn, Black Forest line. We did this one in around Offenburg, but there are more scenarios we want to research. We have the open track scenario. We have these at the high-speed lines at also in Offenburg. We have railway stations. We have this scenario in Offenburg. So lots of these scenarios we already have, like tunnel at the high-speed lines. We thought there must be more scenarios. So we're now at a point where, yeah, we want to get the complete scope of RailTwin and look where we're going to. And now I want to give the floor to Felix so he can give you a glimpse from the engine room out of Offenburg.
Yes. So hopefully this works. Yes, wonderful. Okay, so for me personally, Offenburg is the greatest project. Why? Because I was born in Offenburg, which is an incredible, funny coincidence and really a heart for me. For every picture that I see, for example, here, I know at least dozens of times where I stand on the platform and waited on the train. And so now it's coming to my hometown, which is very nice. Okay, so what I want to talk to you about today is basically one of the concepts, or the key concept overview of RailTwin. So we named this as a multi-source environment, and what we meant with that is that we have different sensoric inputs. So we have images, we have trajectories, we have the point clouds, we have map data, we have everything that we can basically use to create the twin or the model that we use for remodeling. So, of course, this would be a little bit much for today's talk. So we will focus on some of these aspects. And I will just give you a small glimpse, that's why I said a glimpse, of what we can do with that data. So the first thing I want to talk to you about is what we can do with images. And so images in this project we use mainly for detailing. So there is signs and small details that cannot be captured by laser scanners, but are on pictures. But the problem is that pictures are only 2D, and we also need to extract all that information. So what is the idea that we follow through with RailTwin? Well, what we want to create in RailTwin as well is a so-called panoptic data set. Because at the moment, the state of the art for image detection and for object detection is neural networks. And sadly, I must agree, these are the tools that seem to be the most suitable ones. But of course, with every data-driven approach, we need some kind of data set to back it up. So what we need to do is we need to create a data set that can fulfill our requirements for our tasks in that RailTwin project. So there are different ways we can approach dataset creation, and that is that we can have masks, we can locate objects, we can have semantic segmentation where we know where the stuff is, and we also basically can go and combine everything together. So the panoptic means that we have not only the object itself and what type of object it is, but also what kind of background and foreground, things that we cannot count, basically. And the question is, how can we create such a data set? And there is a number of challenges that we face. So the most important challenge is that some of these objects in the data set are very rare. So these come every few meters, every few kilometers, there's one object. For example, there is the switch passing point, which basically tells you when a train can pass another train without colliding. This is a very small image and a very small thing, and it's not viewable on most images. So when we would need to basically go through a data set and make manual labels to create the data set, we would have a lot of images to annotate. And so when we take Offenburg, for example, this would result in 12,000 hours of labeling if we would go for each image for labeling. That is, by the way, 80 person month for those who want to employ someone. Of course, that's not feasible. And what we do is that we have multiple filter stages where we first pre-select, we calculate, we use some knowledge about topology, and then we go deeper into the detailing. And so with that, we are currently working on, and it should work. I cannot see it for detail, but it sounds promising that we can create a data set that concludes 80 classes for image recognitions. So another thing that we use is mobile laser scanning. As you have seen before, maybe in the images, these are basically the 3 laser scans that we use, laser scanners when the train is going. So we use mainly mobile laser scanning systems for capturing geometry. It is kind of accurate. It's not very accurate for the track itself, but for everything else, it's very accurate, or the best thing that we can get. And again, we have the same problem. Data and testing data also for algorithms is extremely rare. So can we do some magic and can convert knowledge into a usable data set? And the answer is, of course, with such a question is, of course we can. And what we'd use for input is the most important parameter, which is the design speed. And then our project partners, Prof, created a generator that is basically using this design speeds from Bavaria that we took to create different objects, different variants of train models with different types of instances that we all want to see in the point cloud. And all these parameters, input parameters, are like varied in a like kind of sensible way. So there's not like that there is a crazy curve, but it's everything that should be in the norm of the Deutsche Bahn. And in the end, we get a lot of variance to actually create a data set. So how do these variants look? So on the left side, you see like some kind of different variants from the top. We get a horizontal alignment, a vertical alignment as well, and we even have super elevation. But that's not all. We also get a 3D representation of the models. We can then use So this is the 3D representation. We can then use these representations to exactly simulate the data source we've seen before. So we've seen this scanner with the butterfly, with the 3 laser scanners, and we can use that in a simulation to simulate not only the points that we catch, but also the error and the noise that we would get in a real capturing scenario. So with this, we basically come to something like this. And because we know from the CAD files which object we hit with the laser, we can actually annotate this object, like this data set, automatically. So before we went to, or we asked Prof to help us with the generation, we did a small test. So this is a sneak peek. As you can see, we have some small issues with the ground, which is flat in the model, but you basically, there's no way you can see a difference like in the model itself here. Like the first results are really promising. So I think I'm a little bit over time, is it? Okay, so there's one thing I want to also like touch a little bit, and that is how we then in the later stage translate the model to like from the trade usable object or a model. Because it's nice if you have all the point clouds and all the labels and we get all this evaluation and then we cannot use it. So how can we make this and basically portion it so different trades can use those for different like applications? And one of the things that really struck me as a mechanical engineer is that in railway design, 3D is not that important. However, some trades still want kind of a small representation or a way where we can annotate information. So for example, Ludwig showed it before, that we can project images onto surfaces and annotate, for example, cracks or special things in the images, which then would be located in a 3D model. So the idea is that we go bottom up with the detection. So we have a classified point cloud, and we go and put bounding boxes around it. So the bounding boxes that we put have a minimum volume. So they're not like normally you see in most softwares aligned with the axis. They actually align themselves. So if there is something like the mast is a little bit bended or something, this box will also bend. Like not the box will bend, but the box will have a shape that is sloped. So this is the first approach, but can we actually go further? And the idea is that we now subdivide the space to get even a better representation. And so what we do is that we go in and we actually subdivide each space to best minimum fit the point model that we put into it. So what we get from that is something that looks like this. So just that you know, this is a 2 divider. So this algorithm in this case uses 2 divisions, so it cannot do concave holes. So this is why we don't get like a perfect modeling here. Well, that's actually, we are dealing with that right now. And what we get is that we have a really slim representation of entities in 3D space. And we also get something that helps us better allocate the object later in the 2D plans. Because the box itself has a better representation as a projection, or can have a better representation of the projection as the points themselves. Because we also have like a contact point to ground. Okay, so to get to summary, what I tried to talk to you about today. So the project itself was absolutely overdue, in our opinion, and that's why we are doing it. It's a very, very interesting endeavor also to combine new technologies, and these lead to new possibilities. The 80 classes that we showed you before, we might maybe not be able to get all of these classes, but we get a big step further in getting a model that can be used for engineering applications. I also showed you some of the concepts that we are using. So there's a lot more to come. And because there's a lot more to come and there's not enough time, I hope that we can talk about later in the questions. I guess the questions will be then moved to the beer section. So thank you.
We are coming to an end of the day, and I'm asking Professor Kolbe to give an outlook of the day and of the Leonhard Obermeyer Center next year.
Okay, thank you very much. So, it's my pleasure to conclude this day's event And before I conclude, I would like to give you a first outlook, because you have seen we did quite a bit of new innovations, of research during the last year. And of course, we have plans for next year and for the next time. And so I would like to quickly have a look at that. So first of all, we are also in collaboration with the BIM World Munich. And so we will also host a session together with our partners, DGNB, and also with a roundtable GIS, which will happen on the 23rd, 24th in November. And the topic of that session is digital methods for sustainable cities and infrastructure. There is also participation and contribution to the Digital Bau in Köln, which is on 15th to 17th February 2022. Again, digitale Methoden der bebauten Umwelt in der Forschung. Okay. We also are collaborating with the Roundtable GIS. I'm also telling that because I'm also chairing that association or that organization. So first of all, we will have the Kommunales GIS Forum. These are things in German, so I think I will switch to German and shortly explain that. Kommunales GIS Forum wird dieses Jahr virtuell stattfinden. Sie können kostenfrei teilnehmen. Warum erzähle ich das hier in dieser Runde? Naja, weil das Thema X-Planung und X-Bau dort ein ganz wesentliches Thema sein wird. Und was vielleicht spannend ist für den einen oder anderen, die Frage Bauleitplanung, wie das digital unterstützt werden kann und vor allen Dingen, wie ist denn der Stand der Einführung in Baden-Württemberg und in Bayern. Das sind eben Themen, die dort vorgestellt werden. Könnte also auch für den einen oder anderen hier interessant sein. Das Zweite ist die Münchner Geoinformatik-Runde. Das ist sozusagen unsere Jahreskonferenz. Da sind vielleicht interessant 3D-Geotechnical und geologische Modellierungen, die dort diskutiert, vorgestellt werden. Es geht generell um das Thema Forschungsdateninfrastrukturen. Das kann also auch unter anderem natürlich auch für das Thema BIM und GIS relevant sein. Und vielleicht auch noch interessant, Fernerkundung, aber ein ganz spezieller Aspekt, nämlich die Analyse von Zeitreihendaten aus Satellitenfernerkundung, was natürlich auch für die Beobachtung der Städte und Verkehr und so weiter relativ wichtig sind. Okay, so I switch back to English. 33. Forum Bauinformatik, that's also something that is being hosted here at TU Munich at the 7th and 9th September, so it's already quite some time to go, but I think it's the annual conference of all the German chairs on civil engineering and computation. And so that will be, I think, maybe, André, I think you will be probably host, or is that together with Frank? I don't know. And the LOC. So, okay, great. Then, actually, we are collaborating and with the platform, Smart Cities and Regions, that was originally founded in the context of the Center of Digitization in Bavaria. And that platform is quite active. And also here we are also participating in that. For example, Frank Petzold is the scientific speaker for the platform Digital Planning and Construction. I'm the scientific speaker for Smart Cities and Regions. And so actually we also are doing quite a bit of activities there. Just a short recap. Currently ongoing and upcoming activities in 2021 are shown there. What I think is important is the platform is still working and launching model region projects. So together with smaller communities, smaller cities in Bavaria, but not just at one location, but really distributed over Bavaria. We are looking forward on introducing the topics of smart district data infrastructure, also digital twins to all these smaller communities. And there is a new round of funding, which will be upcoming soon. So that's also maybe an interesting activity. Also, people can and companies can contribute. Also, municipalities can contribute. So that's some activity going on there. Also, there is a guideline, Leitfaden, which is on how to adopt, how to introduce that SDDI that has been created in collaboration between the platform, between virtual city systems, also the TU Munich and other partners. So, and it has been recently evaluated, and so that will also, all these results and also a revised version of that Leitfaden, that guideline will also be presented in the course of next year. There are different workshops that are also being held, like how to do digital participation for citizens in urban planning projects and different other activities. I will not go into too much detail. Maybe just one more thing. Willi Steinke is the coordinator of that platform, and if you also have questions, you can just ask him, or just also Google for the topic platform Smart Cities and Regions. Again, we are also already have seen that slide in the morning. Not this slide, but a different one from André BORRMANN. I would like to also just simply advertise the starting of our master's course, Information Technologies in the Built Environment. And what is so special about this course is that really all the chairs of the Leonhard Obermeyer Center are participating and contributing. So that means it's not just teaching about and educating about BIM, or not just educating about 3D city models or something, or point clouds, but really all together in the question also how to make use of that. And you probably today learned how important that is to have a look at all these different kinds of tools, methods, and models that are around. And so that's really also something that we want to bring forward. And application will end at the end of April. So if you are interested, or if you know of anybody who might be interested, just forward that information. Then finally, again, these two courses, these courses from the TUM Institute for Lifelong Learning, which are basically organized by LOC, is the BIM professional course that was also mentioned before. The next iteration is going to start soon. And we will also have then the other one, Digital Twins for Cities, and I think also Stefan Drometer already pointed out that we will have a new repetition next year for the Digital Twins for Cities. The first one will be in German language, 5 days. And however, we are currently negotiating and discussing with all the contributors to also have a digital version to be held online. So maybe in May or in June next year. So that's also another possibility to join that. Okay, so that brings me to the end of today's conference. And first of all, I would like to thank you, especially all our members, the premium members. I would also like to thank the associate members and our partners for supporting the Leonhard Obermeyer Center, because we could not do these kind of real combination, you could say, of basic research and especially also applied research. And especially the contact with industry partners helps us very much to learn much more about really the problems that you face. And on the other side, for us, it's also, of course, always a very challenging task to bring latest research results into practice and then really also be confronted with all these things. But however, I think it turned out from what we've seen today that this works out good and nicely, and at least I can tell from the group of professors, we are really very happy with this collaboration, and we really also profiting from that in the same amount as also the PhD candidates, PhD students, and also our other students, master students, and also undergraduates, because many of the tasks and challenges that are brought up here are also playing a role in regular teaching. So we will also take these exercises into the regular courses, into the regular exercises, and so I think that's really something where we all benefit from. And now I will not. Don't want to keep you away longer from a beer and from the get-together, and would like to thank you again, especially also the speakers and the audience for being here, but also for asking questions, and thank you also to the media service for doing all that recording and transmission. I hope you enjoyed it. So see you next year.